Tonight we're going to explore one of the largest challenges humanity has ever encountered. Not a challenge of war, politics, resources, or even survival, but a challenge written into the structure of the universe itself. Imagine standing alone beneath a perfectly dark sky. Above you hangs the pale band of the Milky Way. Thousands of stars shimmer across the darkness. To the human eye, it feels vast. For most of human history, it was vast. Entire civilizations rose and fell beneath those stars. Philosophers wondered about them. Sailors navigated by them. Priests attached stories to them. Scientists eventually measured them, and slowly humanity learnt something astonishing. Those stars were not the universe. They were merely our neighborhood. Now imagine a different scene, far beyond every visible star, far beyond every constellation, far beyond the spiral arms of the Milky Way. Imagine a lone galaxy suspended in darkness. Its billions of stars glow softly against an endless black background. Then imagine another galaxy, and another, not nearby. Not separated by the distance between planets, not separated by the distance between stars, separated by something far larger. An ocean of emptiness so enormous that even light, the fastest thing known to exist, requires millions of years to cross it. This is the universe humanity actually inhabits. A universe composed not merely of stars, but of islands, galactic islands, each containing hundreds of billions of suns, each surrounded by a sea of almost unimaginable emptiness. And tonight's question begins there. If reaching another star is one of the greatest engineering challenges humanity has ever contemplated, what happens when the destination is not another star? What happens when the destination is another galaxy? At first glance, the question almost seems unreasonable. After all, humanity has not yet reached another star. No spacecraft has ever travelled beyond the immediate neighbourhood of the Sun, the most distant human-made object in existence. NASA's historic spacecraft Voyager 1 has been travelling since 1977. For nearly half a century, it has crossed the outer frontier of our solar system. Yet Voyager has travelled less than a single light day from Earth. The nearest star, beyond the Sun, lies more than 4 light years away. Interstellar space alone remains largely unconquered. So why concern ourselves with galaxies? Why think about distances millions of times larger than the ones we already struggle to comprehend? Because sometimes the largest questions reveal something profound about smaller ones. A climber studying Mount Everest learns something about mountains. A sailor crossing an ocean learns something about navigation. And humanity contemplating the distance between galaxies learns something extraordinary about its future. The story is not really about transportation. It is not really about spacecraft. It is not even really about astronomy. It is about limits. The limits imposed by nature. The limits imposed by time. The limits imposed by civilization itself. And perhaps most importantly, whether those limits are truly permanent. Imagine shrinking yourself until the Milky Way becomes visible all at once. From this impossible vantage point, our galaxy resembles a luminous spiral stretching across 100,000 light years. Hundreds of billions of stars swirl around a central core. Nebulae glow like scattered embers. Dark clouds drift between stellar rivers. Entire civilizations could exist inside such a structure without ever knowing the galaxy's true shape. Now pull farther back. The Milky Way begins to shrink. The spiral becomes smaller. Soon it resembles a glowing pinwheel floating in darkness. And then for the first time, another galaxy appears nearby. The Andromeda Galaxy, the nearest major galactic neighbour. Its spiral structure rivals our own. Its stars number in the hundreds of billions. Its diameter exceeds 200,000 light years. It is one of the largest objects in our cosmic neighbourhood, and despite being our closest giant neighbour, it remains approximately 2.5 million light years away. 2.5 million. The number itself sounds manageable. Humans encounter millions constantly. Millions of dollars. Millions of people. Millions of miles. But the phrase, 2.5 million light years, conceals something difficult for the human mind to grasp. Light travels around Earth more than 7 times every second. A beam of light reaches the moon in just over 1 second. It reaches the sun in 8 minutes. It crosses our solar system in hours. Yet even moving at that incredible speed, it requires 2.5 million years to reach Andromeda. When the light arriving from Andromeda tonight first began its journey, early human ancestors were only beginning to walk across African landscapes. Entire species have appeared and vanished since those photons departed. Ice ages came and went. Languages were born and forgotten. Civilizations emerged from nothing and returned to dust. All while a faint stream of light quietly crossed the darkness between galaxies. And Andromeda is close. Disturbingly close. Cosmically speaking, Andromeda is practically next door. Most galaxies reside vastly farther away. Many are tens of millions of light years distant. Others are hundreds of millions. Beyond them lie galaxies whose light began traveling toward us before dinosaurs existed. Beyond those are galaxies whose light started its journey before Earth itself had developed complex life. The universe quickly becomes a place where distance and time merge into the same concept. To look far away is to look backward. To travel far away is to travel across eras. But distance is only the beginning of the story. Because, as astronomers studied these immense separations, they discovered something unexpected. The galaxies were not standing still. The islands were moving, slowly at first, then faster still. The farther away a galaxy appeared, the faster it seemed to be fleeing into darkness. At first, this observation seemed impossible. Surely the universe itself could not be expanding. Surely entire galaxies could not be racing apart across the cosmos. Yet the evidence continued to accumulate, and with it came an unsettling realization. The challenge was no longer simply reaching another galaxy. The challenge was reaching a destination that might be moving away forever. The ocean between the islands was not static, it was growing. And suddenly the greatest obstacle in the story was no longer distance alone. It was time. A resource even more difficult to conquer. One obstacle remained. How large was the universe truly becoming? And what would happen if the space between galaxies continued to expand long after humanity first learned how to cross the stars? The realization did not arrive all at once. No astronomer woke up one morning and discovered the true scale of the universe. Instead, humanity approached the truth slowly, cautiously, almost reluctantly. For centuries, the night sky appeared deceptively simple. The stars seemed fixed. The constellations appeared eternal, and scattered among them were strange, faint patches of light. Some looked like clouds. Others resembled tiny smudges. Through small telescopes, they remained mysterious. Astronomers called many of them nebulae. A Latin word simply meant cloud. No one knew exactly what they were. Some believed they were gas clouds forming stars. Others suspected they might be distant stellar systems. The disagreement would persist for generations, and hidden within that disagreement was one of the most important questions in scientific history. How large is the universe? The answer mattered because humanity's understanding of distance depended entirely upon it. If those faint smudges existed inside the Milky Way, then our galaxy might constitute nearly the entire cosmos. If they existed outside it, then the universe would suddenly become far larger than anyone had imagined. The difference was not small. It was not even large. It was civilization-altering. Imagine living on an island and believing it is the entire world. Every mountain, every river, every forest exists within your maps. Then one day a sailor returns from the horizon with impossible news. The island is not the world. It is only one island among countless others. Everything changes instantly. Geography changes. History changes. Identity changes. Humanity experienced exactly this transformation during the early 20th century. At the time, the Milky Way already seemed enormous. Astronomers estimated that it contained vast numbers of stars. Its dimensions exceeded anything previously imagined. Many scientists understandably assumed that such a colossal structure must represent nearly the whole universe. Why would there be anything beyond it? The galaxy already appeared unimaginably large. Yet observations continued to raise uncomfortable questions. Certain nebulae displayed unusual characteristics. Some appeared strangely structured. Others showed hints of spiral patterns. Through increasingly powerful telescopes, these objects looked less like clouds and more like distant systems. Entire systems, not individual stars, not star clusters, something bigger. the evidence remained incomplete. And so the debate intensified. Arguments filled observatories. Papers challenged previous conclusions. The question became known as the Great Debate. It revolved around a deceptively simple issue. Were spiral nebulae part of the Milky Way, or were they separate universes entirely? At stake was humanity's understanding of reality itself. Then technology intervened, as it often does in the history of discovery. Better telescopes produced better evidence, and better evidence gradually dismantled old assumptions. Across science, this pattern appears repeatedly. A larger lens, a more sensitive detector, a more powerful instrument. Suddenly, an old mystery becomes visible in a new way. The universe reveals another layer of itself, and each layer tends to be larger than the one before. This pattern would prove especially dramatic in astronomy, because every improvement in observation pushed humanity farther from the center of creation. Earth ceased to be the center. Then the sun ceased to be the center. Eventually, even the Milky Way would lose its privileged position. But before that realization arrived, astronomers faced another challenge: distance itself. How do you measure something unimaginably far away? A ruler becomes useless. Even planetary measurements become meaningless. The methods that worked within the solar system could not easily be extended to objects thousands or millions of times farther away. Astronomers needed cosmic yardsticks. Fortunately, nature had provided some. Certain stars change brightness in predictable ways. Their rhythms act like cosmic clocks. By comparing their true brightness to their apparent brightness, astronomers could estimate distance. This breakthrough transformed astronomy. For the first time, scientists could begin constructing a three-dimensional map of the cosmos. And what emerged from those measurements was deeply unsettling. Some objects appeared far beyond the boundaries of the Milky Way. Far beyond. Not slightly beyond. Not marginally beyond. Distances emerged that simply did not fit within existing models. The universe was beginning to outgrow humanity's imagination. Yet even then, many researchers hesitated. The implications were difficult to accept. If these spiral nebulae truly existed outside our galaxy, then space contained not one stellar system, but many. Perhaps thousands. Perhaps millions. Perhaps numbers beyond counting. The scale increase was extraordinary. Imagine discovering that every city on Earth is actually an entire planet, that every nation is actually a solar system, that every continent is actually a galaxy. The mental adjustment required would be immense. Human beings evolved to navigate forests, rivers, and landscapes measured in kilometers. Our intuition struggles with continents. It struggles even more with planets. Galaxies exist so far beyond everyday experience that language itself begins to fail. This is why intergalactic distance feels different from every other kind of distance. The problem is not merely size. The problem is comprehension. A person can imagine driving across a country, flying across an ocean, even traveling to another planet, but another galaxy. The mind searches for familiar reference points and finds none. The scale escapes ordinary experience, and yet the universe is under no obligation to remain understandable. Nature does not adjust itself to fit human intuition. Instead, human intuition must expand, painfully, gradually, generation by generation. The story of astronomy is, in many ways, the story of repeatedly discovering that reality is larger than expected. Every boundary becomes a doorway. Every horizon conceals another horizon. Every answer creates a larger question. By the early decades of the 20th century, astronomers stood on the edge of another such transformation. The evidence was converging. The spiral nebulae were becoming harder to dismiss. The measurements were becoming harder to ignore. Somewhere beyond the familiar stars, entire galaxies appeared to be waiting. Not dozens, not hundreds, potentially countless billions. And if that were true, humanity faced a new problem, because the nearest stars already seemed difficult to reach. The nearest galaxies would be incomparably harder. Interstellar travel suddenly looked like the beginning of a journey, rather than its conclusion. The challenge expanded before humanity had even taken its first step. But the universe had one more surprise waiting. The galaxies themselves were not merely distant. They were distributed across depths of space so vast that ordinary numbers ceased to communicate their scale. Soon, astronomers would begin measuring distances that transformed millions into routine quantities. Soon they would discover that our galaxy was only one member of a much larger cosmic architecture. And with that realization would come a disturbing question. If galaxies are separated by millions of light years, how much empty space actually exists between them? Because it was becoming increasingly clear that the true story of the universe was not written in stars. It was written in the darkness between them, and that darkness was far larger than anyone had imagined. The darkness between galaxies sounds empty. At first, that seems comforting. Empty space suggests simplicity. No mountains to cross, no oceans to navigate, no storms to survive, just emptiness. But the history of exploration teaches a different lesson. The greatest oceans on Earth were not difficult because of what they contained. They were difficult because of how much nothing separated one destination from another. A sailor leaving Europe in the 15th century could not see America. A navigator crossing the Pacific could spend months surrounded by nothing but water and sky. The challenge was not the destination. The challenge was the vast emptiness in between. Intergalactic space takes that principle and expands it to a scale so extreme that even the largest human journeys begin to look microscopic. To understand why we must confront one of the strangest features of the universe, the numbers involved eventually become too large for intuition to process. Human beings are remarkably capable of understanding small quantities. We can picture 10 people, 100 people, even 1,000 people. With some effort, we can imagine 1,000,000. But beyond a certain point, numbers cease to feel different. 1,000,000,000 sounds larger than 1,000,000. 1,000,000,000,000 sounds larger than 1,000,000,000. Yet emotionally, both become abstractions. The mind loses contact with reality. Astronomy lives in that territory, and intergalactic astronomy pushes even farther. Consider the Earth. Its diameter is roughly 12,700 kilometers. That seems large from a human perspective. Walking around the planet would require years. Flying around it requires days. Yet on cosmic scales, Earth is almost invisible. Now expand outward. The distance from Earth to the Moon is approximately 384,000 kilometers. Already the numbers become uncomfortable. The Moon feels nearby in the night sky. Yet nearly every planet could fit between Earth and the Moon. The appearance of proximity is an illusion. Continue outward. The Sun sits roughly 150 million kilometers away. Light requires 8 minutes to travel from the Sun to Earth. Every sunrise is slightly old news. Every ray of sunlight began its journey before most people finish breakfast. Still within the solar system, these distances remain manageable. Signals travel in minutes or hours. Spacecraft travel in months or years. Human planning can still operate comfortably. Then we reach the stars, and everything changes. The nearest star system beyond our own is Alpha Centauri. Its distance is approximately 4¼ light years. That phrase appears simple. 4 light years. Only 4. But hidden inside those words is a number so large that writing it becomes awkward. More than 40 trillion kilometers separate Earth from its nearest stellar neighbor. 40 trillion. Not million, not billion, trillion. Already the scale feels detached from ordinary experience, and yet Alpha Centauri remains one of the closest stars in the entire galaxy. Most stars are far farther away. The Milky Way contains hundreds of billions of them, spread across a structure roughly 100,000 light-years wide. A beam of light moving at nature's maximum speed requires 100 millennia to cross it. Entire civilizations have risen and vanished during far shorter intervals. Human history itself occupies only a tiny fraction of that time span. At this point, many people assume the numbers cannot become dramatically worse. Surely a galaxy must represent the upper limit of meaningful distance. Surely nothing larger matters. Then the galaxies appear. Imagine shrinking the Milky Way until it fits comfortably within your hand. Not a single star. The entire galaxy. Every known human being, every historical event, every mountain, ocean, and civilization, compressed into one luminous spiral. Now place another spiral nearby, the Andromeda Galaxy. To maintain the correct scale, the gap between them would not be a few centimeters. It would be several meters. Most of the model would consist not of galaxies, but of emptiness. The islands are tiny. The ocean dominates. This pattern continues across the universe. Galaxies contain enormous numbers of stars. Yet galaxies themselves occupy only a tiny fraction of cosmic volume. Most of reality is empty space. Not merely empty, overwhelmingly empty. The observable universe resembles an immense web. Galaxies cluster along gigantic filaments. Between them lie cosmic voids, regions so vast that crossing them would take hundreds of millions of years, even at the speed of light. A traveller entering one of these voids might spend longer crossing it than complex life has existed on Earth. And these structures are not rare exceptions. They are fundamental components of cosmic architecture. The universe is less like a crowded city and more like a sparse archipelago scattered across a dark ocean. This realization introduces an uncomfortable possibility. Perhaps distance is not simply a technical challenge. Perhaps distance is the defining feature of reality itself. Throughout human history, progress often reduced separation. Ships connected continents, railroads connected nations, aircraft connected hemispheres, digital networks connected billions of people. Each technological revolution made the world feel smaller. The assumption became almost invisible. Given enough time, humanity learns how to shrink distance. The universe may not share that assumption. Intergalactic space appears almost designed to resist connection. Every increase in scale introduces a larger gap. Every new horizon reveals a wider emptiness. Every achievement uncovers a greater challenge. The pattern becomes difficult to ignore. Imagine a future spacecraft capable of reaching 10% of light speed. Such a machine would represent one of the greatest engineering accomplishments in human history. Entire planetary economies might be required to build it. Yet even that vessel would require roughly 25 million years to reach Andromeda. 25 million years. Long enough for species to evolve, long enough for continents to shift, long enough for civilization to transform beyond recognition many times over. The crew departing Earth would belong to a completely different world than any descendants arriving at the destination. The journey itself would become a chapter of evolutionary history. And this is our nearest major galactic neighbor. The numbers continue to worsen beyond Andromeda. Thousands of galaxies occupy our local cosmic neighborhood. Millions exist beyond it. Billions extend farther still, each separated by distances that challenge not merely engineering, but imagination. Eventually, a deeper question emerges. Perhaps humanity has been asking the wrong question. The challenge may not be how to travel between galaxies. The challenge may be whether any physical object can reasonably cross such distances at all. Because every solution proposed so far depends upon movement. A ship moves. A probe moves. A civilization moves. But what if the distances are so extreme that movement itself becomes the problem? What if the universe is forcing humanity to reconsider the very meaning of travel? The answer would depend upon one unavoidable fact. No matter how advanced a civilization becomes, every journey remains constrained by a single cosmic speed limit. And that speed limit was about to become the greatest obstacle in the entire story. Every civilization dreams of speed. The desire appears almost universal. Faster ships, faster communication, faster transportation, faster access to distant places. Throughout history, often seems synonymous with acceleration. A person traveling across Europe in the Roman Empire measured journeys in weeks. Steam engines reduced those journeys to days. Aircraft reduced them to hours. Digital networks reduced communication to fractions of a second. Each generation inherited a smaller world. Distance did not disappear, but it lost much of its power. The lesson seemed obvious. When confronted by separation, build a faster machine. Yet somewhere deep within the structure of reality, nature had established a boundary, a limit. Not a technological limitation, not an engineering challenge waiting to be solved. A fundamental feature of the universe itself, the speed of light, approximately 300,000 kilometers every second. To human intuition, this velocity appears effectively infinite. Light circles Earth more than 7 times in a single second. A signal can travel from New York to Tokyo almost instantly. Sunlight reaches Earth in 8 minutes. The speed seems enormous because human experience evolved within comparatively tiny environments. Planets feel large. The solar system feels immense. Against those scales, light appears unstoppable. But intergalactic distances reveal a different perspective. They transform light from a symbol of speed into a symbol of limitation. Imagine standing on a cliff overlooking an ocean. A powerful ship waits in the harbour. It is faster than any vessel ever built. Its engines are perfect. Its navigation flawless. Its fuel effectively unlimited. Then someone informs you that the destination lies not across an ocean, but across an entire planet covered by water. Suddenly, the ship's remarkable performance becomes less impressive. The scale of the challenge overwhelms the capability of the vehicle. This is precisely what happens when the speed of light encounters galaxies. Within the solar system, light feels almost magical. Across interstellar space, it remains extraordinary. Across intergalactic space, it begins to look slow, painfully slow. The realization creates one of the most profound shifts in perspective available to any thinking civilization. For centuries, humans viewed light as the benchmark of ultimate speed, and it is. Nothing known travels faster, but ultimate speed does not necessarily mean sufficient speed. The distinction matters enormously. Imagine sending a radio message to the nearest star system. The signal requires more than 4 years to arrive. A reply requires another 4 years. A simple conversation becomes nearly a decade long. Already communication begins to feel strained. Now imagine contacting a civilization in Andromeda. A message requires roughly 2.5 million years to arrive. The response requires another 2.5 million years. A single exchange spans 5 million years. Species could emerge and disappear between question and answer. Civilizations could rise and collapse. Entire evolutionary epochs could unfold during one conversation. Communication in any meaningful sense ceases to exist. The distance has defeated even light itself, and communication represents the easy problem. Travel is far worse. Suppose humanity somehow builds a spacecraft capable of reaching 99% of light speed. The achievement would transform civilization. History would divide into eras before and after its construction. Every previous transportation technology would seem primitive by comparison. Yet despite this astonishing success, the journey to Andromeda would still require more than 2.5 million years from the perspective of observers remaining in the Milky Way. 2.5 million years. No engine failure, no navigation error, no delays, just physics. The speed limit remains undefeated. This creates a remarkable paradox. The faster humanity becomes, the more clearly the scale of the universe reveals itself. A civilization capable of crossing planetary systems discovers the challenge of stars. A civilization capable of crossing stars discovers the challenge of galaxies. Each triumph exposes a larger horizon. Each victory uncovers a deeper obstacle. The story never truly ends. Throughout the 20th century, scientists wrestled with this reality. Some hoped future discoveries might eliminate the problem. Perhaps physics was incomplete. Perhaps faster than light travel remained hidden within equations not yet understood. Perhaps nature contained shortcuts. These possibilities were not unreasonable. History offered many examples of apparent limits eventually overcome. Flight once seemed impossible. Space travel once seemed impossible. Artificial satellites once seemed impossible. Perhaps the speed of light represented another such barrier. But the more researchers investigated, the more stubborn the limit appeared. Instead of weakening, it became stronger. Instead of revealing loopholes, it revealed deeper foundations. The speed of light was not simply a rule. It appeared woven into the structure of space-time itself. The universe seemed organized around it, and that realization transformed intergalactic travel from an engineering challenge into something far more profound. A civilization can build larger engines. It can construct bigger ships. It can gather more energy. But if the speed limit remains fixed, eventually, every strategy encounters the same wall: time. Not technological time, travel time, journey time, civilization time, the kind of time that reshapes societies and species. Imagine a family departing Earth aboard an intergalactic vessel. The parents know they will never arrive. Their children know they will never arrive. Their grandchildren know the same. Generation follows generation. Languages evolve. Cultures transform. Memories fade. The destination becomes mythology, the mission becomes tradition. Eventually, the original civilization may become almost unrecognizable. The ship survives. The people survive. Yet the society that arrives may bear little resemblance to the one that departed. The problem is no longer transportation. The problem has become continuity. How does a civilization remain itself across millions of years? The question seems philosophical. Soon, it becomes practical, because every intergalactic journey eventually collides with it. Yet before humanity could confront that challenge, another realization emerged. The speed of light creates difficulties not only for travel and communication, it creates difficulties for energy. Moving an object close to light speed demands extraordinary amounts of power, and power always comes from somewhere. A civilization attempting to cross the abyss between galaxies would need engines. Those engines would need energy. That energy would need sources. And the numbers involved were beginning to look almost as intimidating as the distances themselves. The story was changing once again. Distance had seemed like the primary obstacle. Then the speed limit appeared. Now an even deeper challenge was waiting behind it. Because reaching another galaxy might not merely require patience. It might require resources on a scale approaching entire worlds. And that realization would force humanity to ask a new question. Not how fast can we travel, but how much of a civilization must be devoted to a single journey across the darkness? At first, energy seems like a problem that civilization can solve. Human history encourages that belief. When wood became insufficient, societies turned to coal. When coal became limiting, they turned to oil and natural gas. Then nuclear energy emerged. Every era appeared to discover a larger reservoir of power than the one before. The pattern suggested an optimistic future. If humanity ever needed extraordinary amounts of energy, surely future generations would simply build larger systems, larger reactors, larger power grids, larger industries. The assumption feels reasonable until the scale of intergalactic travel enters the discussion. Then the numbers begin to change character. They stop sounding difficult and start sounding civilization-sized. Imagine launching a small spacecraft, not a city, not a generation ship, just a modest scientific probe, the kind of machine humanity routinely sends throughout the solar system. Now imagine accelerating that probe to a significant fraction of light speed. The energy requirements immediately become immense, not because the spacecraft is particularly large, not because the technology is primitive, but because velocity itself becomes expensive. The faster an object moves, the more energy must be invested to make it move faster still. Nature does not offer discounts. Every increase in speed extracts a price, and as the destination shifts from stars to galaxies, the bill grows rapidly. A civilization attempting intergalactic travel discovers something uncomfortable. Distance and energy are not separate problems. They are the same problem viewed from different angles. The farther the destination, the more speed becomes desirable. The more speed becomes desirable, the more energy becomes necessary. The more energy becomes necessary, the larger the civilization required to provide it. Eventually, the scale becomes difficult to ignore. An intergalactic mission may not be the project of a nation, or a planet, or even a single solar system. It may become the project of an entire civilization spanning countless worlds. This realization marks a turning point in the story. The challenge is no longer about building a ship. It is about building a society capable of supporting the ship. The focus begins shifting away from engineering and towards civilization itself. But before humanity can understand that transition, we must examine the environment in which it occurs. The Milky Way, our galactic home. For generations, people imagined the galaxy as a destination-rich environment. Hundreds of billions of stars, potentially trillions of planets. Enough opportunities to occupy humanity for millions of years. And that assessment may be correct. A future civilization could spend vast stretches of time exploring only its own galaxy. Colonies might spread gradually outward. New cultures could emerge among distant stars. Entire branches of humanity might evolve independently. The Milky Way alone could contain enough room for countless futures. Yet there is a subtle problem hidden inside this abundance. A galaxy is large, but it is not infinite. From a sufficiently distant perspective, the Milky Way resembles an island, a gigantic island, a magnificent island. Yet, an island nonetheless. And islands possess boundaries. Imagine standing on a shoreline. Behind you lies a thriving civilization. Cities glow in the distance. Ships fill the harbour. Trade routes connect communities. Everything feels expansive. Yet beyond the horizon lies open ocean. The resources of the island eventually end. The territory eventually ends. The familiar world eventually ends. Humanity now faces a similar realization on a cosmic scale. The Milky Way contains extraordinary wealth. But beyond its edges lies something else. Intergalactic space, a realm where stars become rare, where planetary systems become scarce, where support infrastructure disappears, where every journey becomes vastly more difficult. Crossing the galaxy is challenging. Leaving it is something entirely different. The distinction matters because civilizations grow. History repeatedly demonstrates this pattern. Small communities become towns. Towns become cities. Cities become nations. Nations become global networks. Expansion is not guaranteed, but it appears repeatedly throughout human experience. Given enough time, an interstellar civilization might eventually confront a familiar question: what lies beyond the frontier? The frontier in this case happens to be 100,000 light-years wide. Yet eventually even that frontier ends, and then the abyss begins. Picture a future observer standing on a world near the outer edge of the Milky Way. The galaxy stretches across half the sky. Billions of stars illuminate the darkness. Behind them lies the accumulated history of an interstellar civilization. Ahead lies almost nothing. Not emptiness in the absolute sense, not perfect vacuum, but vast regions where useful destinations become increasingly rare. The nearest major galactic target remains Andromeda, 2.5 million light-years away. The observer understands a troubling fact. Their civilization may have conquered the stars. It may have crossed the galaxy. It may command energies beyond anything imaginable today. Yet the next step remains disproportionately harder. The difficulty does not increase gradually, it increases dramatically. This is one reason intergalactic travel occupies a unique place in discussions of the future. Many challenges scale predictably. Building a larger city resembles building a smaller one. Building a larger spacecraft resembles building a smaller one. The same principles generally apply. Intergalactic travel breaks this pattern. The distances become so extreme that familiar assumptions fail. Methods that work within a galaxy may become inadequate beyond it. Strategies that seem practical across thousands of light years become questionable across millions. The universe changes character, and so must civilization. This raises a fascinating possibility. Perhaps intergalactic travel is not primarily a transportation problem. Perhaps it is an evolutionary milestone, a threshold separating different categories of civilization. Much as agriculture transformed hunter-gatherers into settled societies, much as industry transformed agricultural societies into technological ones, intergalactic capability might transform civilizations into something entirely new. A civilization capable of crossing such distances would likely possess forms of coordination, energy production, and long-term planning unlike anything humanity has previously experienced. The journey itself becomes secondary. The civilization capable of attempting it becomes the real achievement. Yet before such a civilization can emerge, it must confront a painful reality. Many proposed solutions appeared promising. Many generated excitement. Many seemed capable of overcoming the abyss for a time. Then the numbers caught up with them. One by one, humanity's early answers to the intergalactic challenge began to reveal fatal weaknesses. Larger engines, faster propulsion, more powerful spacecraft. Each offered hope. Each seemed to bring the destination closer. And each eventually encountered the same relentless obstacle. The universe was larger than expected. Again, the story did not end there. In fact, it was only beginning, because the next phase would become a history of ambitious ideas, remarkable ingenuity, and repeated disappointment. Humanity had started searching for a way across the abyss, but every proposed path seemed to lead toward a deeper problem hidden beyond the horizon. The first solutions were exactly what one would expect from a technological civilization: build a better engine. When confronted with distance, humanity has almost always responded by increasing speed. A faster horse replaces a slower one. A steam locomotive replaces the horse. A jet aircraft replaces the locomotive. A rocket replaces the aircraft. Progress appears as a sequence of increasingly powerful machines. The pattern is so familiar that it feels inevitable. Surely the path toward another galaxy must begin the same way. Build an engine unlike any before it. Build a ship capable of crossing the darkness. At first, the idea seems reasonable. After all, every great journey in history was once considered impossible. Crossing oceans appeared impossible. Circumnavigating Earth appeared impossible. Reaching the moon appeared impossible. Yet eventually, each challenge yielded to engineering. Perhaps intergalactic travel simply awaited a sufficiently advanced propulsion system. For much of the 20th century, scientists and engineers explored precisely this possibility. The results were often remarkable. They imagined spacecraft driven by nuclear reactions, machines powered by fusion, vehicles propelled by beams of light, engines capable of operating continuously for years or even decades. Each concept represented a dramatic improvement over chemical rockets. Each promised access to velocities previously unattainable, and each briefly inspired optimism, because optimism thrives whenever a new capability emerges. Imagine an engineer unveiling a propulsion system capable of reaching 10% of light speed. The achievement would transform civilization overnight. A journey to nearby stars would no longer require geological timescales. Interstellar exploration would become plausible. Humanity's relationship with the galaxy would fundamentally change. Entire futures would suddenly appear within reach. For a moment, the problem would seem solved. Then someone would perform a simple calculation. Andromeda remains 2.5 million light-years away. At 10% of light speed, the journey still requires approximately 25 million years. The celebration would end rather quickly. This became a recurring pattern. Every propulsion breakthrough improved the situation. None improved it enough. A civilization could accelerate 10 times faster. The challenge remained enormous. 100 times faster. Still enormous. Even approaching light speed left the abyss largely intact. The destination stubbornly refused to become close. The scale of the universe repeatedly overwhelmed the scale of the solution. Throughout history, explorers generally benefited from proportional rewards. A stronger ship crossed larger oceans. A larger railway connected larger territories. Greater capability produced greater reach. Intergalactic travel breaks this relationship. Capability grows. Distance grows faster. The universe continuously widens the gap. This realization forced scientists to think differently. The problem might not be the engine itself. The problem might be hidden inside the assumptions behind the engine. Most propulsion systems operate according to a simple principle: carry fuel, expel fuel, move forward. The concept appears throughout rocketry. A spacecraft throws mass backward and accelerates forward. The approach works beautifully within the solar system. Yet intergalactic distances expose a weakness. Fuel has mass. Fuel requires storage. Fuel increases spacecraft weight. Heavier spacecraft require more fuel. More fuel increases spacecraft weight again. The cycle becomes increasingly severe. Engineers sometimes call this the tyranny of the rocket equation. The phrase sounds technical. Its consequences are deeply practical. Imagine preparing for a long road trip. You bring extra fuel. The extra fuel adds weight. Now the vehicle consumes more fuel. So you bring even more fuel, which adds even more weight. Eventually the situation becomes absurd. Intergalactic travel pushes this logic toward extraordinary extremes. A spacecraft designed for millions of years of travel cannot simply carry endless fuel reserves. The mathematics becomes increasingly unforgiving. Soon the vehicle consists primarily of the resources needed to move itself. The mission begins collapsing under its own requirements. Engineers responded creatively. Perhaps the spacecraft could gather resources during flight. Perhaps it could harvest particles from interstellar space. Perhaps giant laser arrays could push light sails across the cosmos. Perhaps fusion reactors could operate continuously for centuries. One idea followed another. Each opened new possibilities. Each extended humanity's reach. Yet none fully escaped the underlying problem. The distances remained incomprehensibly large. Imagine a future civilization constructing a vessel the size of a city. Thousands of people live aboard. Advanced reactors power immense propulsion systems. The ship accelerates. year after year. Its speed gradually approaches a significant fraction of light speed. To its passengers, the machine feels invincible. The engineering appears miraculous. The achievement seems civilization-defining. Then they compare their progress against the distance to another galaxy. The voyage still stretches across spans of time larger than recorded human history. The universe remains indifferent. This indifference is one of the most fascinating aspects of cosmic exploration. Nature does not negotiate. It does not care how impressive a machine appears. It does not care how much effort civilization invested. The laws governing distance remain unchanged. Human ambition encounters reality directly, and reality proves astonishingly large. Yet something important emerged from these failed solutions. Failure often reveals hidden truths. The history of science contains countless examples. An experiment fails. A prediction proves incorrect. A machine performs worse than expected. At first, disappointment follows. Then understanding deepens. The failure becomes more valuable than success. Intergalactic propulsion research produced exactly this effect. Each unsuccessful solution exposed a deeper layer of the challenge. The obstacle was not merely propulsion. The obstacle was duration. The obstacle was continuity. The obstacle was civilization. A sufficiently powerful engine might eventually reach extraordinary speeds, but who would operate it? Who would maintain it? Who would preserve its mission? Who would remember why the journey began? The farther researchers pushed their calculations, the more the focus shifted away from machinery and toward people. An intergalactic spacecraft might remain functional. Could a society remain functional? Could a culture survive? Could purpose survive? These questions proved unexpectedly difficult, because a ship crossing millions of light years would not merely transport travelers, it would transport history. Generations would live and die aboard it. Languages would evolve. Institutions would change. Conflicts would emerge. New traditions would replace old ones. The vessel might survive physically, while the civilization inside transformed completely. The mission could arrive intact. Its original identity might not. And suddenly, the challenge looked very different. The problem was no longer how to build a faster engine. The problem was how to preserve a civilization across intervals of time so vast that entire species might change. The engineering challenge had become a biological challenge. Soon it would become a psychological challenge. And beyond that waited something even larger. Because if a journey lasts longer than civilizations themselves, then the real question is not whether a ship can survive. The real question is whether meaning can survive. The transition happened almost unnoticed. At first, researchers discussed engines. Then they discussed fuel. Then they discussed spacecraft. Eventually, they found themselves discussing entire civilizations. The change was significant, because somewhere along the way, intergalactic travel ceased being an engineering project and became a societal project. The distinction matters. A bridge can be built by engineers. A power plant can be built by engineers. Even a spacecraft can largely be understood as an engineering achievement. But an intergalactic mission demands something larger. It demands a civilization willing to organize enormous resources toward a goal whose reward may not arrive for millions of years. And that requirement introduces a challenge unlike any humanity has previously faced. Energy. Not energy in the everyday sense. Not electricity for homes. Not fuel for vehicles. Civilization-scale energy. The kind capable of reshaping worlds. To appreciate the magnitude of the problem, imagine standing beside a rocket launch. The engines ignite. Flames stretch across the launch pad. The ground trembles. Thousands of tons of fuel disappear within minutes. Even modern spaceflight consumes astonishing amounts of energy. And yet, from a cosmic perspective, such launches are tiny events. The spacecraft leaving Earth today travel at speeds measured in kilometers per second. Intergalactic missions demand something entirely different. They require velocities approaching a meaningful fraction of light speed. The difference is not incremental. It is transformative. The energy requirements rise dramatically. Soon, the discussion begins sounding less like transportation planning and more like planetary economics. Imagine accelerating a city-sized spacecraft, not merely a probe, not merely a crew capsule, an actual settlement, a floating society, homes, infrastructure, agriculture, industry, population. everything necessary to sustain human life independently. Now imagine pushing that civilization toward relativistic speeds. The required energy becomes difficult to describe using familiar language. Power stations are insufficient. Nations are insufficient. Even planetary energy production begins looking small. The mission starts demanding resources measured against entire worlds, and that realization creates what some futurists call the energy civilization wall, a boundary where ambitions stop being limited by technology and start being limited by the total productive capacity of society itself. History offers smaller examples of this phenomenon. Ancient civilizations could not build modern cities, not because they lacked intelligence, not because they lacked motivation, but because their economies could not support the required scale. The challenge exceeded the available surplus. Intergalactic travel threatens to produce a similar effect. The necessary energy may exceed what a planetary civilization can reasonably provide. If so, humanity would need to become something larger before the journey could even begin. This possibility forces a shift in perspective. For most of history, humanity viewed energy as a resource: coal, oil, hydroelectric power, nuclear reactors, future fusion systems. The assumption remained constant. Energy existed to support civilization. Intergalactic ambitions reverse the relationship. Civilization begins existing to support energy production. The mission becomes so demanding that entire economies may orient themselves around it. Imagine a future spanning centuries. Humanity has spread throughout the solar system. Cities occupy Mars. Settlements orbit Jupiter. Industrial complexes harvest resources from asteroids. Billions of people live beyond Earth. At first glance, this civilization appears unimaginably advanced. Yet even this society may view intergalactic travel as prohibitively expensive. The reason is simple. The universe is larger than civilization expands. Every increase in capability reveals a larger frontier. Every solution uncovers a larger requirement. The pattern continues relentlessly. And nowhere is that more evident than in discussions about energy. Consider the sum. Every second, our star releases more energy than human civilization has consumed throughout its entire history. The number is almost absurd. Humanity's collective achievements barely register against the output of a single, ordinary star. This observation inspired an important realization among futurist thinkers. Perhaps advanced civilizations would eventually learn to capture substantial fractions of stellar energy. Perhaps entire stars could become power sources. The idea sounds extravagant, yet compared to intergalactic distances, extravagance becomes surprisingly practical. Civilizations contemplating journeys measured in millions of light years begin considering solutions measured in stellar outputs. The scale of the challenge reshapes the scale of acceptable answers. This intellectual shift appeared repeatedly during the 20th century. As calculations grew more realistic, researchers discovered that conventional assumptions produced disappointing results. Modest improvements were not enough. Incremental progress was not enough. The problem demanded radical increases in capability, and radical increases often require entirely new stages of civilization. This insight produced a profound question. What does a civilization look like when its projects span thousands or millions of years? Human institutions rarely survive even centuries. Empires rise and collapse. Governments change. Economies transform. Languages evolve. Values shift. Yet an intergalactic mission may require continuity across durations far longer than recorded history. Energy infrastructure would need maintenance. Industrial systems would need coordination. Knowledge would need preservation. The challenge becomes less about building and more about sustaining capability, sustaining purpose, sustaining civilization itself. Imagine workers living around a distant star thousands of years from now. They contribute to a project whose completion lies far beyond their lifetimes. Their children inherit the responsibility. Then their grandchildren. Then generations so distant that the founders have become historical myths. The mission persists, not because individuals remain, because institutions remain. Civilization becomes the mechanism through which long-term goals survive. This is one reason intergalactic travel occupies a unique position among future technologies. Most technologies serve individuals directly. Transportation improves daily life. Communication improves daily life. Medicine improves daily life. Intergalactic capability may primarily serve descendants. People living today would never witness the outcome. People launching the mission might never witness the outcome. Entire eras could pass before meaningful results emerge. Such projects require a different relationship with time, a different understanding of responsibility, a different conception of civilization. And yet, even if humanity somehow solved the energy problem, another obstacle remained waiting. Perhaps the most unsettling obstacle so far, because enormous energy can accelerate a ship. Enormous energy can sustain a ship. Enormous energy can preserve infrastructure. But energy cannot solve everything. A civilization might possess all the power required for the journey. It might possess the technology, the resources, the engineering, the industrial capacity, and still fail. Because eventually the mission collides with something that no reactor can generate and no engine can manufacture. Time. Not travel time. Civilizational time. The kind that transforms cultures' identities and meanings. And the longer researchers examined the problem, the clearer it became. The greatest threat to an intergalactic mission might not be external at all. It might come from the people attempting it. At first, time appears manageable. Human beings have always planned for the future. Farmers plant crops they will harvest months later. Builders construct projects that require years. Nations create infrastructure intended to last generations. The ability to think beyond the present is one of civilization's defining characteristics. Without it, cities could not exist. Science could not progress. History itself would become impossible. Yet, intergalactic travel introduces timescales that challenge the very foundations of long-term planning. The problem is not simply that the journeys are long. The problem is that they are longer than almost anything humanity has ever successfully maintained. Imagine standing inside a cathedral, perhaps one of the great stone cathedrals of Europe. Construction often lasted decades, sometimes centuries. Generations of craftsmen worked on structures they knew they would never see completed. The builders accepted this reality. Their lives became part of a project extending beyond them. Modern observers often find this remarkable. It demonstrates an extraordinary capacity for patience and continuity. Now multiply that timescale, not by 2, not by 10, not by 100. Multiply it by thousands, then by millions. The cathedral begins to look instantaneous. The greatest construction projects in history become brief events. Human civilization itself begins to resemble a short-lived phenomenon. This is the environment intergalactic travel creates. A journey to another galaxy may require durations so extreme that historical experience offers almost no guidance. The challenge is no longer reaching a destination. The challenge is remaining coherent while attempting to reach it. Imagine a spacecraft departing the Milky Way. The launch is celebrated across multiple worlds. Scientists speak of history. Politicians speak of destiny. Children watch the departure from distant colonies. The mission enters textbooks. Songs are written. Monuments are constructed. The vessel begins accelerating into darkness. For several centuries, enthusiasm remains strong. Communication continues. The mission retains cultural significance. Then something inevitable happens. New events occur. New discoveries emerge. New priorities compete for attention. The ship gradually becomes less important. Not because the mission failed, because history moved forward. This process has happened countless times before. Ancient wonders once dominated public imagination. Today, many survive only in museums and archives. Great expeditions that once captured global attention eventually became historical footnotes. Human attention shifts naturally. Civilizations evolve. Intergalactic missions must somehow survive that evolution. The difficulty becomes obvious. How does a society maintain commitment to a project lasting longer than any institution it has ever created? How does a mission remain meaningful after thousands of years? What happens after 10,000, 100,000, a million? The questions quickly become uncomfortable because history suggests that continuity is fragile. Empires disappear, religions divide, languages transform, political systems collapse. Even when populations survive, identities often change dramatically. A citizen of ancient Rome would struggle to recognize the modern world. A traveler from the Bronze Age might view contemporary civilization as alien. Yet, those transformations occurred over relatively short periods compared to intergalactic timescales. Now imagine a mission lasting millions of years. The changes become almost impossible to predict. The descendants of the original travelers may not share the same beliefs. They may not speak recognizable versions of the same languages. They may not even understand the mission in its original form. The destination itself could acquire entirely different meanings. At first, this realization appears discouraging. If civilizations inevitably change, perhaps intergalactic travel is impossible. Perhaps continuity simply cannot survive such durations. Yet the story is more complicated, because change is not necessarily failure. Evolution does not automatically destroy identity. Human civilization today differs enormously from ancient societies, yet threads of continuity remain. Ideas survive. Knowledge survives. Stories survive. The challenge becomes understanding which elements endure and which disappear. This distinction fascinated many futurist thinkers. They began asking a new question. What exactly is the thing we are trying to preserve? At first, the answer seems obvious. Preserve the mission. Preserve the technology. Preserve the crew. But deeper examination reveals something more subtle. The mission exists because people give it meaning. Without meaning, the hardware becomes irrelevant. A functioning spacecraft traveling toward a forgotten objective accomplishes little. Purpose matters, and purpose lives inside minds. This transforms the problem again. The obstacle is no longer engineering. It is psychology. Consider a child born aboard an intergalactic vessel. They have never seen Earth, never seen the Milky Way from within, never experienced the civilization that launched the mission. The ship is their entire world. The journey is not an adventure. It is normal life. The destination exists only as an abstraction, perhaps a story, perhaps a lesson taught in school, perhaps a sacred tradition. Would such a person care about the original mission? Maybe. Maybe not. The answer depends upon culture, education, institutions, social structures, the entire architecture of meaning. And suddenly, intergalactic travel begins looking less like transportation and more like civilization design. The mission succeeds or fails based upon how effectively purpose survives across generations. This realization produced a remarkable shift in future studies. Researchers stopped focusing exclusively on spacecraft. Instead, they began focusing on societies. How are stable cultures created? How is knowledge preserved? How are values transmitted? How are institutions maintained? The questions sounded more like sociology than astronomy, yet they emerged directly from the challenge of crossing intergalactic distances. The universe had forced humanity into unexpected territory. Distance became energy. Energy became civilization. Civilization became psychology. And psychology was becoming something even larger, because meaning rarely survives through individuals alone. Meaning survives through communities, families, tradition, shared identities, collective stories. The mission was no longer a machine moving through space. It was a society moving through time. And societies possess their own vulnerabilities. Conflicts emerge, priorities change, factions form, new generations reinterpret old goals. The challenge compounds continuously. One obstacle creates another. One solution reveals a deeper difficulty. The pattern continues. Yet amid these concerns, a new idea began attracting attention. If preserving civilization was the real challenge, perhaps the spacecraft should not merely carry travelers. Perhaps it should carry an entire society from the beginning. Not a crew, not an expedition, a civilization in miniature. A world designed to survive deep time itself. The concept sounded extraordinary, perhaps even impossible. Yet compared to the alternatives, it offered something rare: hope. For the first time, researchers began imagining vessels where generation after generation could live complete lives while the mission continued around them. Not passengers, citizens, not travelers, founders of a moving civilization. The idea would become one of the most influential concepts in the history of interstellar thought, and it emerged directly from a simple realization. The distance between galaxies was not defeating machines. It was defeating time. So perhaps the answer was not to shorten the journey. Perhaps the answer was to build a civilization capable of living inside it. The idea appeared almost absurd when it was first seriously considered. Humanity had spent centuries trying to make journeys shorter. Now some thinkers were proposing the exact opposite. If the distance could not be reduced, perhaps the journey should become a way of life. Instead of transporting people across the abyss, the vessel itself would become a civilization, a floating world, a moving society, a self-contained branch of humanity, traveling through darkness for periods longer than recorded history. The concept eventually became known as the generation ship, and in many ways it represented the first truly honest response to the problem of intergalactic distance. Previous solutions had attempted to defeat the universe. Generation ships attempted to adapt to it. The distinction was profound. Imagine a future many centuries from now. A structure larger than any spacecraft ever built drifts beyond the outer frontier of the solar system. From a distance, it resembles an artificial world. Its illuminated habitats glow softly against the darkness. Agricultural systems occupy vast interior regions. Forests grow beneath engineered skies. Rivers circulate through carefully managed ecosystems. Children are born. Families form. Communities flourish. The inhabitants live ordinary lives, yet every person aboard shares a remarkable circumstance. They exist inside a machine, traveling toward a destination none of them will ever see. The original launch generation is long gone. Their descendants continue the journey, and their descendants continue after them. The ship persists. The civilization persists. The mission persists, at least in theory. This vision captivated scientists, engineers, and writers throughout the 20th century, not because it solved every problem, because it confronted the problem directly. The speed of light could not be exceeded. Distances could not be reduced. Travel times remained enormous. Generation ships accepted these realities and asked a different question. What if humanity learned to live with them? The concept possessed an elegant simplicity. If a voyage requires 10,000 years, create a society capable of surviving 10,000 years. If a voyage requires 100,000 years, create a society capable of surviving 100,000 years. The challenge shifts from propulsion to sustainability, from speed to continuity, from engineering to civilization. For a time, the idea appeared surprisingly promising. After all, humanity already understands many elements required for survival. We know how to grow food. We know how to recycle water. We know how to educate children. We know how to preserve knowledge. The basic ingredients of civilization are familiar. Perhaps the spacecraft merely needed to replicate them. Yet every attempt to expand the concept revealed deeper complications. The first challenge emerged almost immediately: scale. A generation ship cannot be small. Small communities are vulnerable. Disease can devastate them. Genetic diversity becomes difficult to maintain. Economic specialization becomes limited. Social instability becomes dangerous. The vessel requires enough people to function as a real society, not a crew. A civilization. The distinction matters enormously. A crew operates machinery. A civilization creates culture. The farther researchers explored the concept, the more the ship began resembling a world rather than a vehicle. Agriculture became necessary. Education became necessary. Governance became necessary. Entertainment became necessary. Art became necessary. Every element of human life had to accompany the journey. The ship gradually transformed into a miniature planet. And once that realization occurred, new questions appeared. How large should such a society be? 10,000 people, 100,000, a million. The numbers mattered because resilience often emerges from complexity. Large societies can survive disruptions that destroy smaller ones. They possess redundancy, specialization, adaptability. Yet larger populations require larger habitats. Larger habitats require more resources. More resources require larger industrial systems. The vessel grows. The mission grows. The challenge grows. Again and again, the same pattern emerges. Every solution creates a larger problem. Then another difficulty appears. Human beings are not static. Cultures change. Languages evolve. Beliefs transform. Even under stable conditions, societies reinvent themselves across generations. A generation ship would amplify this process. Isolation creates its own dynamics. Traditions drift. Institutions adapt. Unexpected social structures emerge. The civilization that arrives may bear little resemblance to the civilization that departed. At first glance, this seems like failure, but is it? The question became increasingly important. Imagine descendants living aboard a vessel after 20,000 years. Their language differs from that of the founders. Their customs differ. Their politics differ. Their worldview differs. Yet they still maintain a functioning society. They still preserve the mission. They still continue the journey. Has the project succeeded, or has it become something else entirely? The answer depends on how humanity defines continuity, and that question reaches far beyond engineering. It touches philosophy, identity, even the meaning of civilization itself. Throughout history, studies have constantly changed while remaining connected to their past. Modern nations differ dramatically from their ancient predecessors, yet cultural continuity often survives. Perhaps generation ships would follow a similar pattern. Perhaps transformation is not the enemy. Perhaps rigidity is. This possibility encouraged some researchers. A civilization capable of adaptation may survive better than one attempting perfect preservation. The ship would evolve. Its people would evolve. Its institutions would evolve. The mission would persist through change rather than despite it. Yet optimism only carried the concept so far, because eventually the mathematics returned, as it always did. Intergalactic distances remained immense. A voyage lasting thousands of years seemed difficult. A voyage lasting hundreds of thousands of years seemed extraordinary. A voyage lasting millions of years introduced entirely new uncertainties. Could any society remain coherent for such durations? Could any institution survive? Could any mission retain meaning? No historical example offered reassurance. Human civilization itself had existed for only a tiny fraction of the required time span. The challenge exceeded experience. It exceeded precedent. It even exceeded imagination. The generation ship solved one problem by creating another. It transformed travel into civilization. Now civilization itself became the obstacle, and the more researchers examined that obstacle, the more unsettling the implications became. Because the greatest threat to a generation ship might not be mechanical failure, or radiation, or resource depletion. It might be success. A successful society develops its own priorities, its own ambitions, its own identity. Eventually, the descendants may ask a simple question: why continue? Why devote resources to a destination that exists only in ancient records? Why preserve a mission created by people who lived hundreds of thousands of years ago? Why remain loyal to founders who have become mythological figures? The question is difficult to answer because it strikes at the heart of purpose itself. And purpose, unlike fuel, cannot simply be manufactured. The deeper researchers looked into generation ships, the clearer one fact became. The vessel was not carrying people across space. It was carrying meaning across time, and preserving meaning would prove far harder than preserving machinery. The dream remained alive, but its greatest challenge was only beginning to reveal itself. The first generation ship designs treated civilization as a passenger. The ship was the mission. The people were the occupants. The destination was the goal. Simple, understandable, familiar. Then researchers began asking a disturbing question. What if the relationship was reversed? What if the civilization was the mission? What if the ship was merely the container? The distinction appears subtle. In reality, it changes everything. Because once a journey extends beyond ordinary historical timescales, technology stops being the most valuable cargo. People become the most valuable cargo. Not individual people. Civilization itself. Knowledge, culture, language, memory, purpose, the accumulated inheritance of humanity. A generation ship suddenly resembles something very different from a spacecraft. It begins to resemble an archive, a moving repository carrying an entire branch of human civilization through deep time. This realization emerged gradually. Engineers would calculate life support systems. Biologists would calculate ecosystems. Physicists would calculate propulsion requirements. Everything seemed manageable in isolation. Then, sociologists entered the conversation. Historians entered the conversation. Psychologists entered the conversation. And the problem became far more complicated. Machines obey instructions. Civilizations do not. Machines perform predictable functions. Civilizations reinvent themselves. A reactor can be maintained according to specifications. A society cannot. Human beings continuously reinterpret their world. They create new beliefs, new values, new priorities. The process never stops. History itself is evidence. Imagine transporting a citizen from the year 1026 into the present day. The technologies would appear miraculous, the languages unfamiliar, the political systems incomprehensible. Yet the deeper surprise might be cultural. Ideas once considered obvious have vanished. Ideas once considered impossible have become ordinary. Human civilization transforms continuously. Now imagine extending that transformation across 100,000 years, or 1 million. The implications become difficult to predict. The descendants of a generation ship's founders might remain biologically human. Everything else could change. The challenge becomes especially acute because the ship exists in isolation. Isolation creates unique pressures. Communities develop distinct identities. Traditions evolve independently. External correction disappears. On Earth, cultures interact constantly. Trade spreads ideas. Migration spreads ideas. Conflict spreads ideas. Innovation spreads ideas. A generation ship experiences far less exchange. Its civilization develops within a largely closed environment. This can create resilience. It can also create divergence. Over thousands of generations, divergence becomes inevitable. The ship's inhabitants may eventually see themselves not as travelers from Earth, but as members of an entirely separate civilization, perhaps even a separate people. This possibility fascinated many futurist thinkers, not because it represented failure, because it revealed something profound. Intergalactic travel might not spread humanity. It might multiply humanity. Every generation ship could become the origin point of a new civilization, each following its own historical trajectory, each developing unique cultures, unique institutions, unique philosophies. The voyage itself becomes an evolutionary process. Yet this insight creates a new dilemma. If civilizations inevitably change, what exactly should be preserved? The question sounds philosophical. In practice, it becomes essential. Suppose a generation ship carries a vast digital archive. Every language, every scientific discovery, every work of art, every historical record, humanity's entire intellectual inheritance. The archive survives perfectly. Hundreds of thousands of years pass. The descendants still possess access to everything. Has civilization been preserved? Perhaps. Perhaps not. Information alone is insufficient. Knowledge requires interpretation. Interpretation requires context. Context requires culture. A library can survive while its meaning disappears. History offers many examples. Ancient texts survived for centuries unread. Languages vanished. Translated were lost. The information remained physically present. Its significance faded. Generation ships would face similar risks. Preserving data is relatively straightforward. Preserving understanding is much harder. Preserving purpose may be hardest of all. Imagine a classroom aboard a generation ship. A teacher explains the mission. The destination lies millions of light years away. The voyage began thousands of generations earlier. The founders departed a world called Earth. The lesson is accurate. The students listen politely. Yet for them, Earth is almost mythical. No living person has seen it. No living person knows anyone who has seen it. The civilization of origin belongs to an unimaginably distant past. Emotionally, it carries the same weight that ancient kingdoms carry for modern people. Interesting, important, but remote. Now imagine the same lesson repeated after another 100,000 years. The challenge intensifies. The mission survives only if successive generations continue assigning value to it. Meaning must be transmitted continuously. Otherwise, the destination gradually loses relevance. This is why many researchers eventually concluded that governance would become as important as engineering. Not authoritarian control, not rigid social planning, something deeper. Institutional continuity, the ability of a civilization to maintain long-term goals despite constant change. History demonstrates how difficult this can be. Even stable societies struggle to sustain projects across centuries. Political priorities shift. Economic pressures emerge. Unexpected crises intervene. Now imagine extending those challenges across durations longer than human history itself. The scale becomes extraordinary. Yet surprisingly, this realization generated a new form of optimism, because civilization had already demonstrated remarkable resilience. Languages evolve, yet communication survives. Governments change, yet societies continue. Religions transform, yet meaning persists. Humanity possesses an unusual ability to preserve continuity through adaptation. Perhaps that ability could operate on much larger scales. Perhaps civilizations survive not by resisting change, but by absorbing it. The generation ship becomes less like a monument and more like an ecosystem, flexible, adaptive, self-renewing, capable of maintaining identity without remaining identical. This perspective changed the conversation. The mission was no longer about freezing humanity in time. It was about creating conditions under which humanity could continue evolving while preserving a connection to its origins. A delicate balance. Too much rigidity invites collapse. Too much change invites fragmentation. Somewhere between them lies continuity. The challenge resembles steering a civilization through a river of time. The destination matters, but so does the journey, perhaps even more, because the civilization that eventually arrives will not merely inherit the mission, it will embody the mission. The ship itself becomes a historical process unfolding across millennia, a living experiment in whether meaning can survive deep time. Yet even as these ideas matured, a troubling realization emerged. Generation ships addressed the social problem. They addressed the psychological problem. They addressed the continuity problem. But they still depended on one assumption: that the universe would patiently wait for them. And the universe had already given hints that it would not. Far beyond the ship, far beyond the galaxy. Space itself was changing. The galaxies were moving apart. The distances were growing. And soon humanity would discover that the destination was not merely far away. The destination was retreating into darkness. While engineers imagined generation ships and futurists debated the survival of civilization across deep time, another story had already begun reshaping the problem. It started on a mountain. Not a particularly high mountain by modern standards, not a remote wilderness, just a ridge overlooking Southern California. Yet from that mountain, humanity's understanding of the universe would change forever. The year was 1919. The location was Mount Wilson Observatory near Los Angeles, and at its heart stood one of the most powerful scientific instruments ever constructed, the 100-inch Hooker telescope. Today, it appears modest compared to modern observatories. At the time, it represented the frontier of human vision. Through its mirror, astronomers could peer deeper into the cosmos than any generation before them. Among those astronomers was a former schoolteacher, lawyer, and soldier named Edwin Hubble. Few people could have predicted the impact he would have on human history. The universe that Hubble inherited was already enormous. Most astronomers believed the Milky Way constituted the majority of reality. The galaxy seemed vast enough to justify that assumption. Hundreds of billions of stars, immense clouds of gas and dust, distances so large that ordinary language struggled to describe them. Why imagine something larger? Yet Hubble was interested in the mysterious spiral nebulae scattered throughout the sky. Those faint smudges continued provoking arguments among scientists. Were they clouds within the Milky Way, or were they separate stellar systems entirely? The question remained unresolved, but improved telescopes had finally made an answer possible. Night after night, Hubble observed one particular object, a spiral nebula known as Andromeda. Today we call it the Andromeda Galaxy. At the time, its true nature remained uncertain. The object appeared beautiful through telescopes, a faint spiral suspended against darkness. Yet beauty was not enough. Science required measurement, and measurement required evidence. Hubble found that evidence in the form of variable stars. Certain stars brighten and dim according to predictable patterns. By studying those patterns, astronomers can estimate their true luminosity. Once the true brightness is known, distance can be calculated. The method sounds simple. Its consequences were revolutionary. Hubble identified such stars inside Andromeda. Then he performed the calculations. The result was astonishing. Andromeda lay far beyond the boundaries of the Milky Way. Far beyond. Not slightly outside, not near the edge, completely beyond. The spiral nebula was not part of our galaxy. It was another galaxy, an entire galaxy, containing vast numbers of stars, comparable in scale to the Milky Way itself. The implications arrived all at once. Humanity's cosmic home was no longer the universe. It was merely one member of a much larger population. The Milky Way ceased being the cosmos. It became an island, one island among many. This realization ranks among the most important discoveries in history, not because it introduced new technology, not because it improved daily life, because it fundamentally changed humanity's sense of place. For thousands of years, human beings had repeatedly discovered they occupied a smaller position than previously assumed. Earth was not the center. The sun was not the center. Now even the Milky Way lost its special status. The pattern continued. Reality expanded. Human centrality diminished. The universe grew larger and larger and larger still. Yet Hubble's most significant contribution was not finished. In many ways, the discovery of galaxies represented only the first act. The second act would prove even more consequential. As astronomers began studying distant galaxies, they noticed something unusual. The light arriving from them appeared altered. Its wavelength shifted. Colors changed slightly. The effect resembled a familiar phenomenon. When an ambulance passes by, its siren changes pitch. Approaching sounds become compressed. Receding sounds become stretched. The same principle applies to light. Objects moving away appear shifted toward longer wavelengths. Astronomers call this effect redshift. At first, redshifts seemed like a technical curiosity. Then researchers started comparing them. The farther away a galaxy appeared, the stronger the redshift became. The relationship was remarkably consistent. Distance increased. Recession increased. Again and again. Galaxy after galaxy. The pattern refused to disappear. Eventually, Hubble recognized its significance. The galaxies were moving away, not randomly, systematically. The universe itself appeared to be expanding. Imagine standing in a city where every road gradually lengthens. Every building slowly drifts away from every other building. Every neighborhood becomes increasingly distant. Not because anyone is moving through space, because space itself is changing. This was the extraordinary implication emerging from the observations. The universe was not static. It was dynamic, growing, evolving, stretching. For humanity, the consequences were profound. The challenge of intergalactic travel suddenly became much worse. Before Hubble, the problem involved enormous distances. After Hubble, the distances themselves became moving targets. The galaxies were not waiting patiently for future explorers. They were receding. The ocean between the islands was widening. Every passing moment increased the separation. At first, the effect seemed negligible. After all, galaxies move slowly on human timescales. Years pass without noticeable change. Centuries pass without noticeable change. Yet, intergalactic travel does not operate on human timescales. It operates across millions of years. And across such durations, the expansion becomes impossible to ignore. A civilization attempting to cross the abyss must confront a remarkable fact. The destination may be farther away upon arrival than when the journey began. The universe itself participates in the challenge. Distance is not merely an obstacle. It is an evolving obstacle. The realization transformed the entire discussion. Generation ships now appeared even more important. Long-term planning appeared even more necessary. The future became less about overcoming static barriers and more about adapting to a changing cosmos. And the deeper astronomers investigated, the stranger the picture became. Because the galaxies were not simply moving apart, the rate of expansion itself hinted at an even larger story. A story involving the origin of the universe, its future, and a possibility that would eventually force humanity to ask one of the most unsettling questions ever considered. What if some galaxies are destined to become permanently unreachable? For most of human history, the universe was assumed to be permanent. The stars changed little. The constellations appeared fixed. The heavens seemed timeless. Entire civilizations rose and disappeared beneath the same sky. It was natural to imagine that the cosmos itself remained unchanged, a stable stage upon which history unfolded. Hubble's observations shattered that assumption. The universe was not static. It was evolving. And once scientists accepted that fact, a deeper question emerged. If the universe is expanding today, what does that imply about yesterday? The answer led backward through time, farther backward than any civilization, farther backward than any planet, farther backward than any star. Eventually, the logic pointed toward a remarkable conclusion. If everything is moving apart now, then long ago, everything must have been closer together. The expanding universe implied a beginning, not necessarily a beginning in the philosophical sense, but a beginning to the observable cosmic history we inhabit. This realization transformed astronomy. The universe ceased being a static arrangement of objects. It became a process, a story unfolding across billions of years. Galaxies formed, stars ignited, planets emerged, life appeared, civilizations arose. Everything belonged to a larger narrative, and every chapter of that narrative was shaped by expansion. At first, the implications seemed primarily historical. Scientists focused on origins. How did galaxies form? How did stars emerge? How did cosmic structure develop? These questions dominated much of 20th century cosmology, yet hidden within the answers was a troubling consequence for the future. Expansion is not merely something that happened. Expansion is something that continues right now. Every second, every minute, every year, the distances between faraway galaxies increase. Not because galaxies are actively flying through space like bullets, because the fabric of space itself is stretching. This distinction matters enormously. Imagine drawing dots on the surface of a balloon. As the balloon inflates, the dots move apart. No individual dot is driving away under its own power. The surface itself is expanding. The distance increases automatically. The universe behaves similarly on large scales. Galaxies participate in the expansion of space, and over immense periods the effect becomes dramatic. For humanity, the immediate consequences seem insignificant. The solar system remains stable. The Milky Way remains stable. Nearby galaxies remain gravitationally connected. Daily life proceeds unchanged. The expansion reveals itself only across truly vast distances. Yet intergalactic travel exists precisely within that realm. The farther the destination, the more important cosmic expansion becomes. The challenge is subtle at first, then increasingly severe. Imagine a civilization launching an intergalactic mission. The spacecraft travels continuously. Its engines perform flawlessly. Its society survives. Its mission endures. Everything works exactly as intended. Yet during the voyage, the universe quietly alters the geometry of the journey. The destination drifts farther away, not dramatically, not suddenly, gradually, relentlessly. The travelers confront a strange situation. They are making progress and simultaneously losing ground. The universe itself participates in the race. This realization forced cosmologists to think differently about the future. Distance was no longer merely a measurement. It became a dynamic quantity. The map changes while the expedition is underway. For some destinations, the effect remains manageable. The Andromeda Galaxy, for example, is not moving away from us. In fact, it is moving toward us. The Milky Way and Andromeda belong to the same gravitational neighborhood. Their mutual attraction overcomes cosmic expansion. Billions of years from now, the two galaxies are expected to merge. The nearest major galactic destination is therefore becoming closer rather than farther. For a brief moment, this seems encouraging. Perhaps expansion is not such a serious obstacle after all. Then astronomers examined more distant galaxies. The optimism faded. Beyond local gravitational groups, expansion dominates. Galaxies recede. Clusters recede. Entire regions of the universe drift away. The farther outward researchers looked, the faster the recession appeared. Eventually, a remarkable threshold emerged, a distance beyond which galaxies retreat so effectively that reaching them becomes increasingly difficult. Not because engines fail, not because ships fail, because space-time itself continually enlarges the separation. The universe becomes an active participant in isolation. This insight carried profound philosophical implications. For centuries, exploration generally assumes that destinations remain available. An island discovered today can be visited tomorrow. A continent explored today can be explored again centuries later. Humanity unconsciously inherited a belief that geography is permanent. Cosmology challenged that belief. On sufficiently large scales, geography evolves. The cosmic map changes over time. Some destinations become easier to reach. Others become harder. Some eventually disappear beyond practical reach altogether. The concept feels strange because human intuition evolved in a stable environment. Mountains remain where they are. Oceans remain where they are. Galaxies do not necessarily follow those rules. The universe operates on timescales and scales of motion that transcend ordinary experience. And the deeper researchers explored the consequences, the more unsettling the picture became. Expansion alone was already formidable. Then came another discovery, one that altered the future even more dramatically. By the late 20th century, astronomers expected the expansion of the universe to slow over time. Gravity should gradually reduce the rate. After all, galaxies attract one another. Matter pulls matter. The cosmic expansion ought to decelerate. Observations suggested otherwise. Careful measurements revealed something extraordinary. The expansion was accelerating, not merely continuing. Accelerating. The galaxies were not simply drifting apart. The process was speeding up. The cause remains one of the great mysteries of modern cosmology. Today, it is often associated with what scientists call dark energy. Whatever its ultimate nature, the effect is unmistakable. The universe is expanding faster with time, and suddenly the future looked very different. A steadily expanding universe is challenging. An accelerating universe is transformative. It introduces the possibility of cosmic horizons, regions that future civilizations may never reach, regardless of technological sophistication. Doors that gradually close. Not because anyone chooses to close them, because the universe itself evolves. The implication for intergalactic travel was difficult to ignore. Humanity was not simply confronting distance. Humanity was confronting a moving deadline. The cosmic ocean was widening. The islands were separating. And somewhere far ahead in the story waited a profound question. If the universe continues accelerating forever, how much of it will ultimately remain accessible? The answer would force civilization to reconsider its future on the largest scale imaginable. By the middle of the 20th century, the problem had become impossible to ignore. Distance was enormous. The speed of light imposed limits. Galaxies were moving apart. The expansion of the universe appeared to be accelerating. Every time humanity examined the challenge more closely, it seemed to grow. Yet history contains a remarkable pattern. When confronted by larger obstacles, human imagination often grows larger as well. This tendency produced one of the most fascinating chapters in the story of cosmic exploration. If ordinary engineering could not solve the problem, perhaps civilization-scale engineering could. Few individuals embodied this shift in thinking more clearly than Freeman Dyson. Dyson was not primarily interested in intergalactic travel. His influence came from something broader. He possessed an unusual willingness to think on enormous scales. Scales measured not in years, but millennia. Not in cities, but planets. Not in planets, but stars. During the 1960s, Dyson began asking a deceptively simple question. How would a truly advanced civilization use energy? The question seems unrelated to intergalactic travel. In reality, it touched the heart of the problem, because every challenge humanity had encountered eventually led back to energy. Greater speed required greater energy. Larger spacecraft required greater energy. Longer missions required greater energy. Civilization itself increasingly appeared constrained by access to power. Dyson recognized an important fact. Stars produce extraordinary amounts of energy. The sun releases more power in a single second than human civilization consumes over immense periods of time. Yet nearly all of that energy radiates uselessly into space. From a cosmic perspective, humanity intercepts only a tiny fraction of its star's output. An advanced civilization, Dyson suggested, might do something different. Instead of living merely around a star, it might surround the star with vast structures designed to collect its energy. The concept eventually became known as a Dyson sphere. Strictly speaking, Dyson himself imagined something closer to a swarm of orbiting habitats and collectors, rather than a solid shell, but the broader idea captured public imagination. A civilization could expand until it harvested a substantial portion of an entire star's energy output. At first glance, the proposal sounds fantastical, yet the mathematics behind it are surprisingly straightforward. If intergalactic ambitions require civilization-scale energy, then perhaps civilizations eventually become star-scale. The logic follows naturally. The larger the challenge, the larger the infrastructure required to confront it. Dyson's insight changed the conversation. Previously, discussions focused on spacecraft. Now attention began shifting towards civilizations themselves. What if the key to crossing immense distances was not building better ships? What if it was building larger societies? Imagine humanity thousands of years in the future. The solar system has become densely populated. Millions live in orbital habitats. Industrial systems harvest asteroids. Energy collectors orbit the sun in vast numbers. The total productive capacity of civilization exceeds anything imaginable today. From this perspective, an intergalactic mission begins looking different. Still difficult. Still expensive. But no longer inconceivable. The mission becomes one project among many, rather than the defining effort of an entire species. This represented a profound conceptual breakthrough. The challenge remained enormous. Humanity's scale could also become enormous. The universe had forced a new way of thinking. Not bigger machines, bigger civilizations. And Dyson was hardly alone. Throughout the 20th century, thinkers increasingly explored what later became known as cosmic engineering. The phrase refers to projects so large that they reshape entire planetary systems or stellar environments. Projects measured in astronomical units rather than meters. At first, these ideas sounded speculative, yet they emerged directly from practical considerations. Intergalactic travel repeatedly demanded resources beyond conventional scales. Eventually, conventional scales stopped being useful. Imagine attempting to cross an ocean with a rowboat. The solution is not a slightly larger rowboat. The solution is a fundamentally different category of vessel. Similarly, crossing the abyss between galaxies may require fundamentally different categories of civilization. This insight produced an unexpected side effect. It transformed the search for extraterrestrial intelligence. If advanced civilizations construct enormous energy-collecting systems, perhaps those systems become observable. Perhaps alien civilizations reveal themselves not through radio messages, but through engineering. Astronomers began considering the possibility. Maybe the universe contains societies far older than humanity. Maybe some already command stellar energies. Maybe some have confronted the same challenge now facing us. The possibility was intriguing. Yet, observations offered no clear answers. The sky remained silent. No unmistakable evidence appeared. The mystery deepened. If civilization-scale engineering is theoretically possible, where are the civilizations? The question became famous. Why does the universe appear so empty? Why do the galaxies seem so quiet? The issue would eventually become known as the Fermi paradox. And although it extends beyond the subject of intergalactic travel, it introduces an important perspective. Perhaps the challenge is even harder than it appears. Perhaps advanced civilizations are rare. Perhaps survival across cosmic timescales is difficult. Perhaps distance itself acts as a filter. The possibilities remained uncertain. Yet Dyson's work left a lasting legacy regardless. He helped shift humanity's thinking from individual technologies to civilization-wide capabilities. The distinction would prove crucial, because the deeper researchers explored intergalactic travel, the more obvious it became that no single invention could solve the problem. No miraculous engine, no perfect spacecraft, no isolated breakthrough. The challenge demanded an entirely different relationship with scale. Civilizations would need to think like ecosystems, like planetary networks, like long-duration historical processes. And once that perspective emerged, attention naturally turned toward a more radical possibility. If larger civilizations are not enough, perhaps the structure of space-time itself must be reconsidered. Perhaps the answer lies not in gathering more energy. Perhaps the answer lies in changing the geometry of the journey. The idea sounded extraordinary. For decades, it remained largely theoretical. Yet some of the most respected physicists in history found themselves drawn toward it, because every conventional solution seemed to encounter the same wall. Distance remained too large, time remained too long, the universe remained too vast. And so humanity began investigating possibilities that once belonged almost entirely to imagination. Wormholes. Warp drives. Shortcuts through space-time itself. Concepts that seemed impossible. Concepts that perhaps were impossible. Yet when the challenge spans millions of light years, even impossible ideas become worthy of examination. By the late 20th century, the conversation had reached a peculiar stage. Every conventional solution remained trapped by the same fundamental constraint: distance. No matter how efficient the engine, no matter how vast the energy supply, no matter how resilient the civilization, the abyss between galaxies persisted. The universe continued presenting the same answer. Travel requires time, and intergalactic travel requires extraordinary amounts of it. For many thinkers, this conclusion was unacceptable, not because they doubted the science, because they understood the implications. If the speed of light represents an absolute limit, then even the most advanced civilizations may remain confined to relatively small regions of the cosmos. Galaxies become islands, clusters become archipelagos, the observable universe fragments into separated domains, connection becomes increasingly difficult. The future begins to resemble isolation. Naturally, some researchers asked whether another path existed. Not a better engine, not a larger civilization, a different relationship with space itself. The idea was ancient in spirit. Human beings have always dreamed of shortcuts, mountain passes, canals, railroads, air routes. Whenever geography presents an obstacle, people search for ways around it. Perhaps space-time possessed similar opportunities. The first serious hints emerged from an unexpected source. Not engineering, not astronomy, mathematics. Specifically, the mathematics of gravity. In 1915, Albert Einstein introduced the theory of general relativity. The theory transformed humanity's understanding of gravity. Space was no longer an empty stage. Time was no longer a separate backdrop. Together, they formed space-time, a dynamic structure capable of bending, stretching, and evolving. The idea sounded abstract. Its consequences were profound. Planets move because space-time curves. Stars shape the geometry around them. Galaxies influence the motion of light itself. Gravity becomes geometry, and once geometry enters the story, a fascinating possibility appears. If space-time can bend, perhaps it can bend dramatically. Perhaps it can fold. Perhaps distant regions can become connected. Perhaps shortcuts exist. The first mathematical hints arrived in the 1930s. Einstein and physicist Nathan Rosen explored unusual solutions within general relativity. These solutions later became associated with what popular culture calls wormholes. The concept is often explained using a sheet of paper. Imagine 2 points drawn on opposite sides. Traveling across the surface requires crossing the entire distance. But fold the paper. The points touch. A shortcut appears. The journey becomes dramatically shorter. The analogy is simple. The mathematics behind it is not. Yet the possibility captured imaginations immediately. A wormhole seemed to offer exactly what intergalactic travel required. Not greater speed, reduced distance. Instead of crossing millions of light years, a civilization might traverse a shortcut connecting distant regions of space-time. The appeal was obvious. The challenges were equally obvious. Unfortunately, mathematical possibility does not guarantee physical reality. Many solutions exist on paper that nature never implements. Researchers quickly discovered troubling complications. Most wormhole models appeared unstable. Tiny disturbances could destroy them. Others seemed to collapse too quickly for anything to pass through. Some required exotic forms of matter never observed in practical quantities. Again and again, the universe resisted easy answers. The pattern felt familiar. Every promising solution revealed a deeper obstacle. Every breakthrough generated a complication. The story continued. Yet wormholes were not the only idea. By the second half of the 20th century, another possibility emerged. Instead of shortening the route, perhaps space-time itself could be manipulated. This concept eventually became associated with warp drives. The basic intuition is surprisingly elegant. Relativity prohibits objects from moving traveling through space-time faster than light. It says much less about space-time itself. The universe already provides examples. Cosmic expansion stretches space. Galaxies can become separated faster than light because space between them grows. Nothing locally violates relativity. The geometry changes. This observation inspired a provocative question. Could a sufficiently advanced civilization engineer similar effects? Could space-time be compressed ahead of a vessel and expanded behind it? Could a spacecraft effectively ride a wave of distorted geometry? In 1994, Mexican physicist Miguel Alcubierre proposed a mathematical model demonstrating such a possibility. The idea became famous almost immediately, not because it provided a working warp drive, because it showed that general relativity permitted surprising structures. For the first time, faster-than-light travel seemed less obviously impossible. The excitement was understandable. A warp drive appears to offer liberation from the tyranny of distance. Galaxies no longer seem unreachable. The universe suddenly feels smaller. Then the calculations continued, and once again difficulties appeared. The energy requirements looked extraordinary. Some versions demanded quantities comparable to entire stars. Others required exotic negative energy. Many remained purely theoretical. The closer researchers examined the concept, the more elusive practical implementation became. Yet something important had changed. The conversation was no longer restricted to propulsion. Humanity had begun questioning the geometry of reality itself. This shift represented a major intellectual milestone. The challenge had grown so large that it forced civilization into the deepest levels of physics. Questions once confined to abstract mathematics now possessed practical relevance. Could space-time be engineered? Could shortcuts exist? Could the structure of reality itself become technology? No definitive answers emerged. Even today, the subject remains uncertain. Some possibilities survive mathematically. Others appear increasingly unlikely. The universe guards its secrets carefully. Yet the investigation produced an unexpected benefit. It clarified the true nature of the challenge. Intergalactic distance is not merely an engineering problem. It is a physics problem, a civilization problem, a philosophical problem, perhaps even an existential problem. The search for impossible physics revealed the boundaries of current understanding, and boundaries possess value. They show where knowledge ends. They indicate where future breakthroughs might occur. For decades, researchers explored those boundaries. Some hoped for shortcuts. Some hoped for new discoveries. Some hoped nature might contain hidden opportunities. Perhaps it still does. But as the 21st century progressed, a different realization began emerging. Maybe the solution was not defeating distance. Maybe the solution was learning to work with it. Maybe the answer had been hiding in plain sight all along. Not in exotic physics, not in impossible machines, but in the way civilization itself grows. And when that realization finally arrived, it transformed the entire question. Humanity stopped asking how to leap between galaxies. Instead, it began asking how civilizations spread through the universe across deep time. The difference would change everything. For more than a century, humanity had approached the problem from the same direction. The destination was impossibly far away. Therefore, the journey needed to become faster. The assumption seemed natural. It was rooted in every previous chapter of exploration. When continents appeared, distant ships became faster. When nations appeared distant, transportation improved. When planets appeared distant, rockets emerged. Speed felt synonymous with progress. Yet every attempt to apply that logic to galaxies produced disappointment. The numbers remained overwhelming. The speed of light remained stubborn. The universe remained vast. And perhaps most importantly, every solution depended upon a hidden assumption that one civilization must complete the journey. Eventually, researchers began questioning that assumption. What if the problem had been framed incorrectly from the beginning? The realization emerged gradually. Not from a single discovery, not from a revolutionary experiment, from the accumulation of many observations. Generation ships revealed the importance of continuity. Cosmic engineering revealed the importance of scale. Expansion revealed the importance of time. Together they suggested a different way of thinking. Civilizations are not static objects. They grow. They spread. They reproduce. The comparison to biology was difficult to ignore. Life on Earth did not conquer the planet through extraordinary speed. It succeeded through persistence. Generation after generation, expansion after expansion, adaptation after adaptation. The process required immense time, yet it transformed an entire world. Perhaps civilization operates similarly. Imagine a single settlement established on a nearby star system. The colony survives. It prospers. Centuries pass. Eventually, that colony establishes 2 additional settlements. Those settlements create more, then more, then more. No individual voyage spans extraordinary distances. No spacecraft crosses millions of light years. Yet civilization gradually expands. The frontier moves outward. The process resembles the growth of a forest. One tree becomes many. The forest advances not through speed, but through multiplication. This idea represented a profound breakthrough. Not because it made intergalactic travel easy, because it made it realistic. For the first time, the challenge appeared compatible with known physics. No warp drives required, no wormholes required, no violations of relativity required, only time. A great deal of time. Imagine humanity 100,000 years from now. The solar system is merely one node in a growing network of civilizations. Nearby stars host settlements. Trade occurs between systems. Knowledge flows across interstellar distances. The process remains slow by human standards. Yet over long periods, slow processes become powerful. The frontier continues advancing, a few light years at a time, then dozens, then hundreds, then thousands. The scale steadily increases. The key insight is deceptively simple. A civilization does not need to leap across a galaxy. It only needs to move from one reachable destination to the next. The distinction changes everything. The galaxy becomes a chain of opportunities rather than a single, overwhelming challenge. Intergalactic travel may operate according to the same principle. Consider the local group. This is the collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller companions. The entire structure spans millions of light years. At first glance, it appears forbiddingly large. Yet, from the perspective of a civilization expanding gradually over deep time, the distances become less intimidating. The challenge transforms from crossing one enormous gap into navigating a sequence of manageable steps. This is where the breakthrough truly emerges. Human beings instinctively evaluate journeys through individual lifetimes. Can I make the trip? Can my children make the trip? Can my society make the trip? Cosmic civilization demands a different perspective. The relevant unit is no longer the individual, not even the nation, not even the species. The relevant unit becomes civilization itself. Civilization survives beyond generations, beyond governments, beyond cultures, perhaps even beyond biological forms. Once that shift occurs, the timescales begin looking different. 1,000,000 years remains immense. But a civilization capable of enduring for millions of years may not view the number as prohibitive. The challenge becomes historical rather than impossible. The distinction is subtle. It is also transformative. History offers an interesting analogy. Ancient humans eventually populated every continent on Earth. No single expedition accomplished the feat. No master plan guided the process. Expansion occurred gradually. Groups moved. Settlements formed. Generations continued the movement. The frontier advanced. Eventually, the entire planet became inhabited. From the perspective of any individual traveler, the outcome would have seemed impossible. From the perspective of history, it became inevitable. Some futurists began wondering whether the galaxy might experience a similar process. Not through conquest, not through centralized planning, through gradual expansion. Civilization spreading because civilization naturally expands into available opportunities. The implications were remarkable. The Milky Way might eventually become interconnected, not in a few centuries, not in a few millennia, across much longer durations, yet still vastly shorter than the age of the universe. And if one galaxy can be crossed this way, perhaps multiple galaxies can as well. The concept introduces a new relationship with distance. Previously, every light year appeared as an obstacle. Now light years become stepping stones. The destination ceases to dominate the discussion. The process becomes more important than the end point. This is one reason the breakthrough felt so significant. It did not defeat the laws of physics. It embraced them. The universe remained vast. Relativity remained intact. Expansion remained real. Nothing fundamental changed. Only perspective changed. And sometimes perspective is the most powerful technology available. Yet even this breakthrough carried complications. The universe was not standing still. Expansion continued. Dark energy continued. The cosmic geography itself continued evolving. The strategy of gradual expansion appeared promising. Would it remain fast enough? Could civilization spread before portions of the universe drifted permanently beyond reach? The question introduced a new urgency. For the first time, intergalactic travel no longer looked impossible. It looked like a race. Not a race against rival civilizations, not a race against technological limitations, a race against cosmic time itself. And the deeper researchers explored that possibility, the more extraordinary the future began to appear. Because if civilization could spread through the universe the way life spreads through an ecosystem, then humanity's destiny might not depend on a single ship at all. It might depend on a network of civilizations extending across deep time, a living structure measured not in planets or stars, but in galaxies. Once the breakthrough became clear, the problem changed shape. The question was no longer, how do we send a ship to another galaxy? The question became, what kind of civilization can gradually reach another galaxy? At first glance, the distinction seems minor. In reality, it marks one of the most important transitions in the entire story. For centuries, humanity imagined exploration as a sequence of journeys. A vessel departs. Travelers endure hardship. A destination is reached. The narrative begins and ends with the voyage. A galactic civilization operates according to different principles. The civilization itself becomes the vehicle. Its settlements become the engines. Its institutions become the guidance system. Its continuity becomes the fuel. The frontier advances not because one ship succeeds, but because countless communities persist. Imagine standing on Earth 10,000 years in the future. The night sky still glows with familiar constellations. The moon still circles overhead. The sun still dominates the heavens. Yet humanity has changed dramatically. Permanent settlements occupy nearby stars. Industrial networks connect multiple systems. Information moves between worlds. Distinct cultures have emerged across interstellar space. Some societies preserve ancient traditions. Others have developed identities entirely their own. The descendants of humanity are no longer concentrated on a single planet. They form a distributed civilization. A civilization measured not in cities, but in star systems. The remarkable aspect of this vision is its plausibility. No impossible technologies are required. No violations of physics are necessary. The process depends upon repetition. One settlement becomes 2. 2 become 10. 10 become 100. The expansion remains slow from the perspective of individuals. Yet history repeatedly demonstrates the power of cumulative processes. Forests spread this way. Languages spread this way. Civilizations spread this way. Small actions repeated across immense timescales become transformative. Consider the Milky Way itself. The galaxy contains hundreds of billions of stars. Only a fraction may possess habitable environments. Even that fraction represents extraordinary abundance. A civilization does not need every system. It needs pathways, networks, stepping stones. The galaxy begins resembling a vast landscape rather than an empty void. This shift in perspective changes everything. Previously, distance dominated the conversation. Now connectivity becomes equally important. The frontier is no longer a line. It is a web. New settlements create new opportunities. Every colony becomes a launch point for future expansion. Every generation contributes to a process larger than itself. The pattern resembles history on Earth. Ancient trade routes connected distant communities. Roads linked cities. Ports linked continents. Eventually, entire civilizations emerged from networks rather than isolated settlements. A galactic civilization may evolve similarly. The scale changes. The underlying principle remains recognizable, yet building such a civilization introduces challenges of its own. Distance still matters. Communication remains slow. The speed of light continues imposing limits. A message traveling between stars may require years. Across larger networks, delays become even more significant. The result? is profound. No galactic government can operate like a modern nation-state. The distances are too large. Information travels too slowly. Centralized control becomes increasingly difficult. Instead, future civilizations may resemble ecosystems. Independent communities connected by shared history, culture, and exchange. Unity emerges through relationships rather than direct administration. This possibility fascinated many futurists, not because it simplifies the future, because it complicates it. Humanity's descendants may not form a single civilization in the conventional sense. They may form a family of civilizations, related, interconnected, distinct. The implications extend far beyond politics. Culture itself changes. Imagine a colony orbiting a star thousands of light years from Earth. Generations pass. The local environment shapes traditions. The local economy shapes institutions. The local history shapes identity. Eventually, the inhabitants develop perspectives unlike those of their distant relatives. The process is not failure. It is adaptation. Diversity becomes a feature rather than a flaw. Over time, entire branches of human civilization emerge. Each contributes to the larger network. Each follows its own path, and collectively, they advance the frontier. This realization introduces a remarkable possibility. Perhaps the future of humanity resembles a living galaxy, not a single empire, not a unified state, a dynamic collection of societies linked across space. Some thrive, some decline. New communities emerge, old communities disappear. The network evolves continuously. History becomes interstellar. At this scale, the concept of exploration begins changing again. Early explorers crossed oceans. Future explorers may cross stars. Yet the largest journeys belong not to individuals, but to civilizations. The movement becomes generational, historical, distributed across vast spans of time. The distinction matters because it reframes the challenge of intergalactic travel. The destination no longer appears as an isolated objective. It becomes a natural extension of expansion. The frontier gradually approaches neighboring galaxies, not through a dramatic leap, through persistence, through continuity, through countless small advances accumulated across ages. Yet one obstacle remained, perhaps the most important obstacle since the discovery of cosmic expansion: time. Not merely travel time, not merely civilizational time, deep time. The timescale on which galaxies evolve. Stars die. Cosmic structures transform, because even a civilization spreading successfully through the Milky Way must eventually confront a larger reality. The universe itself is changing. Galaxies move. Clusters evolve. Cosmic horizons shift. The future does not wait patiently for expansion to occur. The map continues changing while civilization advances across it. And this introduces an extraordinary question. If humanity eventually becomes a galactic civilization, how far can that civilization ultimately spread before the universe itself places a final boundary in its path? The answer would require thinking not in centuries, not in millennia, not even in millions of years. It would require thinking across epochs so vast that civilization begins to resemble a geological force, a process unfolding across deep cosmic history. Human beings are creatures of short horizons. A decade feels significant. A century feels historical. 1,000 years feels ancient. Most of our institutions, our stories, and even our intuitions are built around these scales. Yet the universe operates according to a very different clock. Stars live for billions of years. Galaxies evolve across billions more. Cosmic structures emerge and transform over intervals so vast that human history barely registers against them. To understand the future of intergalactic civilization, humanity must learn to think on those scales. Deep time. Not merely long time, deep time. The kind of duration that changes the meaning of permanence. Imagine standing beside a mountain. The stone appears eternal. Generations come and go, while the mountain remains. Yet, given enough time, even mountains vanish. Wind reshapes them. Water erodes them. Continents shift beneath them. What appears permanent reveals itself as temporary. Deep time changes perspective. The same principle applies to galaxies. Today, the Milky Way seems enduring, a fixed feature of reality, yet the galaxy itself is part of an ongoing process. Stars form. Stars die. Spiral arms evolve. Neighboring galaxies interact. Nothing remains unchanged forever. A civilization planning intergalactic expansion must operate within this dynamic environment. The realization is both daunting and liberating. Daunting because stability cannot be assumed. Liberating because immense amounts of time become available. Human beings often focus on the limitations imposed by distance. Deep time reveals the opportunities created by duration. Consider a civilization expanding at modest speeds, not near light speed, not using exotic physics, simply moving steadily from one star system to another. The process may appear slow, painfully slow from an individual perspective, yet over millions of years, slow expansion becomes extraordinary. A frontier advancing by a tiny fraction of a light year each year eventually spans entire regions of a galaxy. The arithmetic is relentless. Time multiplies capability. This insight represents one of the most important intellectual rewards in the entire story. Distance dominates human intuition because we experience short lifetimes. Deep time reverses the equation. Over sufficiently long durations, persistence becomes more important than speed. The universe remains vast. Civilization gains time. Imagine a settlement established around a nearby star. Centuries pass. The settlement flourishes. It launches additional colonies. Those colonies repeat the process. No single generation witnesses the full expansion. Yet history accumulates. Millennium after millennium, the network grows. The frontier advances. Eventually, regions once considered unimaginably distant become integrated into a larger civilizational landscape. The process resembles biological evolution. No individual organism transforms a species. Countless generations collectively produce extraordinary outcomes. Civilization may function similarly. The future emerges not from singular events, but from sustained continuity. This perspective alters the emotional character of intergalactic travel. Earlier sections of our journey focused on impossibility. Distances appeared overwhelming. The speed of light appeared restrictive. Expansion appeared discouraging. Deep time introduces a different mood. Patience. The universe remains difficult. The challenge remains immense. Yet the obstacle begins looking historical rather than absolute. History becomes the medium through which civilization moves. And history, unlike propulsion, has no fixed speed limit. The deeper researchers explored this idea, the more they realized that civilization itself might be a mechanism for converting time into reach. A society lasting 1,000 years can accomplish things impossible for a society lasting a century. A society lasting 1,000,000 years enters an entirely different category, not merely more capable, fundamentally different. This possibility encouraged long-term thinking among futurists. What institutions survive deep time? What cultural practices promote continuity? What forms of governance remain stable? The questions sound political. They are actually cosmological, because the future accessibility of the universe may depend upon them. Imagine two civilizations. One possesses extraordinary technology but collapses repeatedly. The other advances more slowly but maintains continuity. Across short intervals, the first appears superior. Across millions of years, the second may dominate. Persistence compounds. The universe rewards endurance. History offers countless examples. Species survive not because they are strongest in any given moment, but because they adapt across generations. Civilizations may follow the same principle. The implication is profound. The future of intergalactic expansion may depend less on spectacular breakthroughs and more on sustained resilience. A civilization capable of surviving deep time becomes a force unlike anything humanity has previously encountered. Not because it moves quickly, because it remains. Yet deep time introduces another surprising consequence. Identity begins changing. Imagine descendants of humanity living 50 million years in the future. The number is difficult to comprehend. 50 million years ago on Earth, mammals were only beginning their rise after the extinction of the dinosaurs. Now reverse the perspective. 50 million years forward. Languages would transform beyond recognition. Cultures would transform Biology itself might transform. The descendants of humanity may differ dramatically from their ancestors, perhaps through natural evolution, perhaps through deliberate modification, perhaps through technologies not yet imagined. The question becomes unavoidable. What exactly continues across such intervals? What remains human? The issue is not merely philosophical. It directly affects intergalactic civilization. Expansion across deep time may create countless branches of humanity. Distinct societies, distinct identities, distinct futures. The network continues growing, yet its participants become increasingly diverse. The frontier spreads not only geographically, but culturally. A galaxy inhabited by humanity's descendants may not resemble a unified civilization. It may resemble an ecosystem of civilizations. Connected, related, different. The realization is extraordinary. The challenge of crossing galaxies gradually transforms into a challenge of preserving continuity amid diversity. The universe changes, civilization changes, humanity changes. Yet, the process continues. Expansion becomes a historical phenomenon unfolding across cosmic timescales. And this brings us to a remarkable conclusion. The greatest obstacle may never have been distance. The greatest obstacle may have been perspective. Human beings naturally think in lifetimes. The universe demands thinking in epochs. Once that transition occurs, new possibilities emerge. The abyss between galaxies remains immense, yet it no longer appears completely inaccessible. A path exists, slow, patient, grounded in known physics, built from continuity rather than speed. But one final question remained. Even if civilization learns to cross deep time, can deep time outrun the universe itself? Because cosmic expansion had not stopped. The galaxies continued drifting apart, and somewhere ahead waited the ultimate test of humanity's patience. Would persistence be enough, or would the universe eventually become too large, even for civilization itself? For centuries, humanity's relationship with distance followed a familiar pattern. Find a barrier, invent a faster way across it. The formula worked repeatedly. Roads shortened journeys, ships connected continents, railways compressed nations, aircraft compressed the planet, digital networks compressed communication itself. Every success reinforced the same intuition. Distance is a problem, speed is the solution. By the time humanity began contemplating galaxies, that intuition had become deeply embedded. It felt almost self-evident. Surely the path forward required greater velocity, greater acceleration, greater propulsion. Yet after generations of investigation, a remarkable conclusion began emerging. The universe might not be conquered through speed at all. The most realistic path toward intergalactic reach does not defeat physics. It cooperates with physics. This realization represents the culmination of everything we have explored so far. The speed of light remains intact. Relativity remains intact. Cosmic expansion remains intact. No miracle technology appears. No hidden loophole suddenly rescues civilization. Instead, humanity discovers something subtler. The distinction between moving quickly and spreading effectively. The difference is profound. Imagine a drop of ink placed in water. The individual molecules move slowly, yet over time the ink spreads throughout the container. The process succeeds not because any molecule travels extraordinarily fast. It succeeds because countless small movements accumulate. Civilization may function similarly. The future of intergalactic expansion may depend less on individual voyages and more on distributed growth. This perspective changes the emotional character of the challenge. Earlier generations imagined a heroic expedition. One vessel, one mission, one dramatic crossing of the abyss. The reality may be quieter, less cinematic in the traditional sense, and far more powerful. The civilization expands gradually through networks of settlements. Each community becomes a center of activity. Each center produces new opportunities. Expansion proceeds through multiplication. The process resembles ecology more than exploration. At first glance, this seems almost disappointing. Where is the great leap? Where is the legendary voyage? Where is the triumph over impossible distance? Then the scale becomes apparent. Imagine a civilization expanding steadily for 10 million years, not rushing, not racing, simply continuing. The frontier moves outward, star by star, region by region. Eventually, the accumulated effect becomes extraordinary. Entire galaxies become connected, not through centralized control, through continuity. The achievement is no less impressive because it occurs gradually. In many ways, it is more impressive because it endures. History offers useful parallels. The spread of life across Earth required immense time. The spread of agriculture required immense time. The spread of civilization required immense time. Many of the most transformative processes in history succeeded through persistence rather than speed. The universe may reward the same strategy. This insight also reshapes the meaning of technology. Earlier sections focused on engines, reactors, spacecraft, megastructures all remain important, yet they increasingly appear as supporting systems. The true breakthrough lies elsewhere, in the ability of civilization to survive, to reproduce, to adapt, to maintain continuity across generations. Technology becomes the infrastructure supporting those capacities. The destination becomes secondary to the process. This is perhaps the deepest lesson hidden inside the challenge of intergalactic distance. The universe repeatedly redirects attention away from machines and back towards civilization itself. Every apparent solution eventually becomes a question about people. Can societies endure? Can institutions survive? Can meaning persist? Can cultures adapt? These questions prove more important than propulsion, because propulsion without continuity accomplishes little. A civilization capable of surviving deep time gains access to opportunities unavailable to short-lived societies. The universe becomes navigable not through speed, but through endurance. And endurance changes everything. Imagine descendants of humanity living across thousands of star systems. Their cultures differ, their histories differ, their technologies differ, yet they remain connected through overlapping networks of exchange and memory. The structure resembles a living organism. Information flows, resources flow, ideas flow. The civilization expands organically, not because anyone directs every movement, because continuity creates momentum. The process begins looking remarkably resilient. Local failures occur. Individual settlements disappear. Unexpected catastrophes emerge. The network survives. Redundancy protects it. Diversity strengthens it. The civilization becomes difficult to extinguish. And once that threshold is crossed, a fascinating possibility emerges. Distance loses much of its power, not because galaxies become closer, because civilization becomes larger. The relationship reverses. Earlier in history, humanity measured itself against the universe. Now the civilization begins measuring itself across the universe. The perspective changes. The scale changes. The meaning of exploration changes. Yet even this achievement carries a shadow, because while civilization expands, the universe continues evolving. Expansion accelerates. Cosmic horizons shift. Galaxies drift farther apart. The race continues. A patient civilization can cross extraordinary distances. Can it cross them quickly enough? The question becomes increasingly important. Some regions remain accessible today. Will they remain accessible forever? Cosmologists began examining the issue with growing urgency. Their calculations revealed a startling possibility. The observable universe is not a permanent landscape. It is a temporary one. Galaxies visible today may become unreachable in the distant future. Entire regions of cosmic geography may gradually disappear beyond practical access. The implication is remarkable. Humanity may exist during a special era, an era when large portions of the universe remain available, not because they are easy to reach, because they have not yet drifted beyond reach. The realization transforms intergalactic expansion into something more than exploration. It becomes an encounter with cosmic opportunity, a window, a temporary opening in the history of the universe. And windows do not remain open forever. The farther researchers pushed their calculations, the clearer the picture became. Civilization may eventually learn how to spread across galaxies. Civilization may learn how to survive deep time. Civilization may learn how to work with the laws of physics rather than against them. Yet even then, a final boundary remains, not imposed by engineering, not imposed by energy, not imposed by society, imposed by the future evolution of the universe itself. And that boundary would force humanity to confront the largest question of all. How much of the cosmos can ever truly become home? For most of this journey, distance appeared to be the central character. Every challenge traced back to it. Every proposed solution attempted to overcome it. Every obstacle seemed rooted in the immense emptiness separating galaxies. But distance was never acting alone. All along, another force had been quietly reshaping the story. Time. Not human time. Not civilizational time. Cosmic time. The time through which the universe itself evolves. And as astronomers looked farther into the future, they discovered something extraordinary. The universe is not merely expanding. It is gradually changing which destinations can ever be reached. This realization emerged from one of the strangest consequences of modern cosmology. The observable universe is not the same thing as the accessible universe. The distinction sounds technical. Its implications are profound. Imagine standing on a shoreline at sunset. Far across the water, islands are visible. You can see them clearly. Their existence is undeniable. Yet visibility does not guarantee accessibility. The tide may be rising. The currents may be strengthening. The water may be widening faster than any boat can cross. Eventually, the islands remain visible but unreachable. Cosmology suggests something similar may be happening on a universal scale. Galaxies can remain observable while gradually slipping beyond practical reach. The reason lies in accelerated expansion. For billions of years, the universe has been growing larger. Distances between remote galaxies have increased. More recently, astronomers discovered that this process is accelerating. The cosmic ocean is widening ever faster. At first, the effect appears abstract. Human timescales are far too short to notice meaningful changes. Civilizations can rise and fall without observing any obvious difference. Yet across billions of years, the consequences become dramatic. Imagine humanity surviving for unimaginable durations. Millions of years, tens of millions, hundreds of millions. The descendants of civilization continue expanding. New settlements appear. Networks grow. Galaxies become increasingly interconnected. Everything seems promising. Then the geometry of the universe begins asserting itself. Some destinations remain reachable. Others become increasingly difficult. Eventually, entire regions drift beyond practical access. The frontier stops expanding in certain directions, not because civilization failed, because the universe changed. This possibility introduces one of the most remarkable concepts in modern cosmology. The cosmic event horizon. The phrase resembles something from navigation. In many ways, it is. Just as sailors once confronted physical horizons beyond which visibility disappeared, future civilizations may confront cosmological horizons beyond which access disappears. The galaxies do not vanish. They continue existing. Light continues traveling. History continues unfolding. Yet the separation grows so rapidly that meaningful contact becomes impossible. The effect is difficult to visualize because everyday experience provides no equivalent. Nothing on Earth behaves this way. Mountains do not retreat faster than travelers can approach. Cities do not drift permanently beyond reach. The universe introduces a new category of separation, a separation created by the evolution of space-time itself. Imagine a civilization observing a distant galaxy. The galaxy contains stars, planets, perhaps life, perhaps civilizations of its own. The observers know it exists. They can study its light. They can measure its motion. Yet no realistic journey can ever arrive there. The destination belongs to reality, not to possibility. The distinction is subtle. It is also heartbreaking. For generations, exploration has carried an implicit promise. If something exists, perhaps it can eventually be reached. Cosmology weakens that promise. Existence does not guarantee accessibility. The universe contains more than any civilization can ever visit, more than any civilization can ever influence, more than any civilization can ever truly know. At first, this conclusion appears discouraging. It seems to diminish humanity's future. Yet another interpretation exists. The accessible universe remains astonishingly large. Even after accounting for cosmic horizons, the available territory exceeds comprehension. Thousands of galaxies, millions of star systems, trillions upon trillions of worlds. The scale remains extraordinary. The challenge is not scarcity. The challenge is finitude. The universe is vast. It may not be infinitely available. This realization changes the nature of long-term strategy. If accessibility gradually declines, then timing matters. Civilizations capable of expanding earlier gain opportunities unavailable later. The future becomes path-dependent. Choices made across millions of years influence which regions remain connected. History begins shaping cosmology. The interaction is remarkable. For the first time, civilization's trajectory becomes linked to the large-scale evolution of the universe. Not because humanity controls cosmic expansion, because humanity must respond to it. Imagine two hypothetical futures. In one, civilization remains confined to a single planetary system. The accessible universe steadily shrinks around it. More galaxies drift away. More opportunities disappear. The cosmic horizon closes gradually. In another future, civilization expands. Networks spread. Settlements multiply. Connections form across vast distances before those distances become prohibitive. The accessible universe remains larger because civilization reached it in time. The contrast is striking. The universe does not simply present opportunities. It presents windows of opportunity, and windows eventually close. This perspective transforms intergalactic expansion into something deeper than ambition. It becomes stewardship. A civilization inherits access to a portion of reality. What it does with that inheritance matters. The challenge is no longer merely technological. It becomes historical, cultural, philosophical. The future depends not only on capability, but on vision. Can civilization think on scales large enough to appreciate what is at stake? Can it value opportunities whose consequences unfold across billions of years? Can it act before the horizon changes? The questions feel enormous because they are. Yet they emerge naturally from a simple observation. The galaxies are moving apart, and they are not waiting. The realization brings our journey toward its final stage. Distance remains immense. Physics remains uncompromising. The universe remains vast. Yet humanity now possesses a clearer understanding of the challenge. Not a challenge of engines, not a challenge of ships. A challenge of civilization, of patience, of continuity, of deep time, and ultimately of meaning. Because once we understand which parts of the universe can be reached, a final question remains. Why reach them at all? Tonight we began with a deceptively simple observation. The distance between galaxies is worse than you think. At first, the statement sounded like a problem of measurement. Millions of light years, billions of kilometers, vast expanses of emptiness, numbers so large they resist intuition. Yet as our journey unfolded, the meaning changed. Distance turned out to be only the surface of the challenge. Behind it waited energy. Behind energy waited time. Behind time waited civilization. And behind civilization waited something even deeper: meaning. Because every question about the future eventually returns to a question about purpose. Why should humanity care about galaxies it may never reach? Why invest effort into futures unfolding across millions of years? Why concern ourselves with horizons so distant that no individual will ever see them? The answer begins with perspective. Throughout history, stimulates expanded their sense of belonging. Small communities became nations. Nations became global societies. Humanity gradually learnt to think beyond immediate surroundings. The process was neither simple nor inevitable, yet it happened. Each expansion enlarged the circle of concern. The universe may invite a similar transformation, not because exploration is mandatory, not because destiny demands it, because understanding changes what is possible. Imagine standing beneath the night sky, the same sky observed by countless generations before us. The stars appear calm, the galaxies appear distant, everything feels permanent, yet we now know that the cosmos is dynamic. Galaxies move, stars evolve, the universe itself changes. The sky is not a static picture, it is a moment within a vast unfolding story. Humanity occupies one chapter of that story, a very small chapter, yet not an insignificant one. For the first time in the history of Earth, a species has emerged that can understand the larger structure in which it exists. The atoms composing our bodies originated inside ancient stars. The elements supporting life were forged through cosmic history. Every person alive today participates in processes stretching back billions of years. The realization carries a peculiar emotional quality: humility. Not despair, not triumph, humility. The universe is larger than any civilization, older than any civilization, likely destined to outlast any civilization. Yet civilization remains meaningful precisely because it exists within that vast context. A single human life is brief. A civilization lasts longer. A species longer still. The universe endures longer than all of them. Meaning emerges not from permanence, but from participation. This insight becomes especially important when considering intergalactic distance. The galaxies are unimaginably far apart. Most of them will never be visited by people alive today. Many may never be visited by humanity at all. The accessible universe possesses limits. The cosmic horizon exists. Reality contains boundaries. Yet boundaries do not eliminate significance. A library remains meaningful despite containing more books than one person can read. A forest remains meaningful despite containing more trees than one person can count. The universe remains meaningful despite containing more destinations than one civilization can reach. The challenge is not ownership. The challenge is relationship. How does humanity relate to a cosmos vastly larger than itself? Earlier generations often answered through mythology. Later generations answered through philosophy. Modern civilization increasingly answers through science. Not because science removes wonder, because it deepens it. The true scale of the universe is more remarkable than any ancient imagination could have anticipated. The galaxies are larger. The distances are greater. The history is deeper. The future is longer. Reality repeatedly exceeds expectation, and perhaps that is the most important lesson hidden within intergalactic distance. The universe is not obligated to fit human intuition. Again and again, humanity has discovered that reality is stranger, larger, and more subtle than expected. Every major breakthrough has expanded the horizon. Every answer has revealed a larger question. The process continues, even now. Perhaps future generations will discover principles we have overlooked. Perhaps new forms of civilization will emerge. Perhaps entirely new relationships with time, identity, and exploration await. The story remains unfinished. That unfinished quality matters. When people discuss the future, they often imagine conclusions. The first interstellar voyage, the first galactic civilization, the first contact with another intelligence. Yet history rarely provides final endings. It provides continuations. One achievement becomes the foundation for another. One frontier reveals the next. The challenge of intergalactic distance may never truly disappear. It may simply evolve. Future civilizations may confront questions we cannot yet formulate, just as modern cosmology would have seemed unimaginable to ancient astronomers. The horizon keeps moving. The story keeps growing. And that observation brings us back to the beginning. The distance between galaxies is worse than you think. Much worse. It is larger than intuition. Larger than engineering, larger than ordinary history. The abyss between the islands of the cosmos is real. The universe does not offer easy pathways across it. Yet the story does not end there, because humanity possesses something unusual: the ability to imagine futures beyond individual lifetimes, the ability to cooperate across generations, the ability to transform knowledge into continuity. These capacities may ultimately matter more than speed, more than propulsion, more than technology itself. Civilizations survive not because they move quickly. They survive because they endure. And endurance changes the meaning of distance. A journey that appears impossible within a lifetime becomes conceivable across millennia. A challenge that appears overwhelming within a century becomes approachable across deep time. The universe remains vast. Humanity remains fragile. Both statements are true, yet fragility does not imply irrelevance. A candle remains fragile. Its light still matters. Earth itself occupies a tiny corner of one galaxy among hundreds of billions. Yet from that small corner emerged a species capable of contemplating the entire cosmos. A species capable of measuring galaxies, imagining futures, asking questions, seeking understanding. Perhaps that is the most remarkable fact of all. Not that the universe is large, but that part of the universe has become aware of its own size. And somewhere far beyond the horizon, beyond the galaxies we may one day reach, and beyond the galaxies we never will, the story continues. The stars continue burning, the galaxies continue drifting, the cosmos continues unfolding, and humanity's chapter, however long it lasts, is still being written.